Good afternoon, everybody. We'll get started in about 1 minute. All right, good afternoon. Welcome back, everybody, for our last half of the conference, or last quarter of the conference. We're going to start off session 7, which is about severe weather forecasting, with Bill Bunting, who is our third and final keynote speaker for today. Bill Bunting is the Chief of Forecast Operations at the Storm Prediction Center up in Norman, Oklahoma. So we expect nothing but perfection from this keynote, knowing Bill. But before you get started, Bill, just wanted to show you your handy dandy plaque we're going to be mailing you, and an appreciation of you taking the time and preparing this talk for us, and just one way we can say thank you, even though it's a small way. But expect that in the mail hopefully sometime in the next week or so. With that, I'll give it to Bill Bunting and he can start us off.
Okay. Okay. I'll go ahead and start from the beginning, talk a little faster. Appreciate the invitation to be here this afternoon and speak to you on behalf of the work going on here at the Storm Prediction Center. I just wanted to acknowledge the significant contributions from some folks here at SPC, our director, Russ Schneider, the Science Support Branch Chief, Patrick Marsh, and the Storm Prediction Center, Sue Israel Urak. The topics I wanted to cover, again, it's just a partial list of things that we're working on here at the SPC. Include some changes to the convective outlook that have occurred since 2014, just put that in perspective. Talk about some of our work in developing severe storm probabilistic timing guidance and our plans to eventually make publicly available more frequent day one convective outlooks, isolating corridors of higher risk. Also want to talk a little bit about our efforts to fill the watch warning gap, the emphasis on the meso-beta scale with some of our products. And then finally end with a quantitative impact-based decision support services, a concept that we're working on right now with FEMA, but may very well spread with time as we gain confidence in its usefulness. And all of this I want to talk about is in the context of a facets paradigm. Facets is forecasting a continuum of environmental threats. And it's a paradigm that really marks a transition away from periodic deterministic products, outlooks, watches, warnings, into a more continuous probabilistic stream. And in fact, here's a great summary slide for facets if you're not familiar. I would encourage you to check out Lance Rothfuss and his co-authors in the October 2018 AMS Bulletin, an excellent overview of facets. But in essence, it combines the benefits of NWP, forecaster expertise, and other tools, post-processed guidance, to develop a robust quantification of the weather hazard risk. This helps to inform more consistent IDSS and ultimately better decision-making by our core partners. I'll talk mostly about facets in a severe paradigm, but the notion of facets certainly extends beyond severe weather. This is a graphic that was produced by Heather Lazarus at NCAR. It does a great job of explaining or graphically conceptualizing the product stream from outlooks, days in advance, to watches and warnings in the minutes preceding the event, and then the rough approximation of uncertainty, which decreases with time. For those of us who have forecast for any length of time, we know that uncertainty doesn't always get smaller as the event approaches. Sometimes actually the uncertainty increases. But in a general sense, this is the flow. Well, over the past 5 or 6 years, work here at the SPC has been focused on this left-hand side of the spectrum here, in the outlooks, days in advance, trying to refine our communication and improve our use of probabilistic information. And I want to just go over some of those with you. Back in late 2014, we introduced a couple of things that were substantial in terms of changes to our outlooks. Number one was the introduction of a 15% area in the day 4 through 8 outlook that was in addition to the pre-existing 30%, which is a pretty high threshold at that time range. The original idea behind the day 4 through 8 outlook was to give advance notice of outbreaks, and that's a pretty high bar. And with 15%, we're now able to capture perhaps events that are not quite outbreak scale, but are significant. And certainly 4 through 8 outlook has been really beneficial. What you see there is the day 4 outlook preceding the Easter Sunday outbreak of this year, and the corresponding reports in the lower left. On the right-hand side is the day 3 outlook preceding the next Sunday after the Easter Sunday outbreak, which is the April 19th severe weather event, again across much of the Gulf coastal states. The introduction of marginal and enhanced replaced the C-text that existed prior to that. And also, we heard from many emergency managers and other meteorologists that some events didn't seem like slight risk. And the reason for that was that slight risk encompassed a pretty broad probabilistic range. And not everyone looked at the probabilities. They just saw a slight risk and they went on about their day, even though the probabilities were on the higher end of the spectrum. So by adding the enhanced or enhanced slight really is what it refers to, and we were better able to delineate the higher threat areas in our categorical outlooks. The other change we made earlier this year was the transition from total severe probabilities in the day 2 outlook to individual hazard probabilities. We did that in late January of this year, again reflecting increased skill on the part of SPC forecasters to not just say what the threat level is for the following day, but what particular threats or hazards were contributing to that overall risk. And this has been very well received, and it was only a few weeks after we started that we got some really good tests with the Easter Sunday and the following Sunday severe weather events. Corresponding with those changes, we also introduced some graphics. These were developed by Patrick Marsh here at SPC. And these, given the importance of IDSS nationally within the National Weather Service, having the ability to quickly take an SPC Outlook graphic and utilize it for CWA, county warning area, state-based, FEMA region, or even a broader scale on days when severe weather outlooks, public severe weather outlooks are issued, has been a very useful tool. We've gotten some great feedback on that as well. All of these changes were really obtaining internal and external decision support. They really helped drive the conversation. And so it was important for us working together with those who rely on our forecast, both within and outside of the National Weather Service, to make the forecast as clear as possible and to really make them as specific in terms of the actual hazards so that people could prepare accordingly. This is just an example of 3 different severe weather events and a mix of both National Weather Service, local office graphics, television graphics, and also graphics and text on various social media platforms. So it's important to be sure that we're communicating consistently and as effectively as possible. The established CAM guidance that we look at in the weather enterprise, not just here at SPC, but all of us, the CAM guidance is getting for CAM-enabled ensembles that really promise the possibility of high-resolution probabilistic severe weather outlooks. And we're certainly taking advantage of that here at the Storm Prediction Center. The high-resolution ensemble forecast, or HREF, was the operational implementation of the Storm Scale Ensemble of Opportunity, which was initially provided on our SPC website publicly back in 2012. So we have a long history of several years of providing what amounts to an ensemble of opportunity. These are deterministic models that were put together to extract the benefits of looking at this guidance in an ensemble mode. And this has been very well received and continues to be an important tool, not only here at the SPC, but across the enterprise in terms of anticipating severe weather and getting forecast to align with that potential. The HREF has been used for several years now in the NOAA Hazardous Weather Testbed. That's an event that occurs every year for 5 weeks, 5 one-week sessions here in Norman, adjacent to the Storm Prediction Center and right next door to the Weather Forecast Office. So it's a great synergistic collaboration of forecasters, researchers, modelers, folks that all have a hand in improving our capabilities. And as you can see here, this is 2020 when the HWT was actually virtual because of the COVID pandemic. The HREF performance was at the top, and really subjectively, based on the participants' input, outperformed the experimental research ensemble. So it's really a high bar and quite an accomplishment for the National Weather Service to have this operationalized and now supported 24/7. So with the HREF as a background, how can we take characteristics of guidance and lead to better forecasts, certainly higher resolution forecasts? And one of the ways that we are working to do that is the development of severe weather timing guidance. The SPC forecasts do a very skillful job of telling you where severe weather is expected over a 24 or whatever the remaining valid time of the outlook is for that period. But in terms of being more specific about the timing in particular areas, that's an area where we can employ forecaster expertise and CAM guidance to really hone in on that. And so the timing guidance really leverages the HREF to add probabilistic information on an hourly basis. And it requires 2 inputs. Number one is the SPC Day 1 convective outlook with the forecaster determined thunderstorm outlook boundaries. We then convert that into continuous probabilities, not the stair-step probabilities that you see on our webpage. And then we develop calibrated 4-hourly hazard guidance that's updated hourly from a combination of the HREF for the timing and storm attributes and the SREF for the environmental variables. And so really what this does is it optimizes the human in or over the loop and combines what we do better with what automation can do really well. I will say that right now, this is available within NOAA.gov domain computers as a prototype, and we really want feedback. Our ultimate goal would be to get this into the hands of local National Weather Service weather forecast offices to use in their forecast and IDSS tools. And so switching just a bit from the timing guidance into, well, first of all, let me show you an example of the timing guidance. This is a case that was a pretty interesting case, 23 February 2019. A cluster of tornadoes in the lower Mississippi Valley on the fringes, for the most part, of a moderate risk that we had in effect. This was the day that we had a significant tornado in Columbus, Mississippi, unfortunately with loss of life, 1 fatality, and 19 injuries. This is the high-resolution guidance that was produced that day, and this is a still image just to show you what it was for tornado probabilities at its peak. And you can see there that the percentages are highest in the area where, if you can see the red dots, we did have tornadoes occur. And this is an example of again, the good performance overall of the HREF in providing skillful timing guidance. And because it's produced on a grid, you can click on any grid point and you can see the time series there towards the upper left over the Pacific Northwest that will show you the SPC hazard probabilities over the course of time. So this represents sort of a unique way to convey severe weather risk, and I think it will have some utility in impact-based decision support services because, again, you can show the temporal variation in the risk as you go through the convective day. And then it also shows the categorical risk. So this really, I think, lends some unique opportunities to communicate this information to our partners. So here's the SPC probabilistic risk for tornadoes as issued that day, and an animation of the HREF or the timing guidance probabilities, again, showing pretty good correlation with the increasing probabilities and the reports that show up there in the red dots. A couple of events towards the end that were outside, but again, this guidance is going to be as good as the CAM guidance, which, while skillful, isn't of course perfect. Another example of how you could click on Columbus and get a good idea of the timing of that, where the probabilities are highest, and we've annotated where the tornado watch was in effect and then where the tornado occurred. So certainly an example of the utility of this timing guidance. Another example, this is from Easter Sunday of this year, showing again the variation, the east-west or west-to-east progression, of the threat. So in the left side, you see where the tornadoes occurred relative to this event over the lower Mississippi Valley, again showing a peak around 22 UTC in close agreement with what actually occurred. And then as the event moved east overnight, you can see that the probabilities increase towards the southeast and getting closer to the Carolinas towards the early morning hours. And again, the probabilities there reflect that accordingly. So some skill and again, great potential utility as we move forward with impact-based decision support services. Here's another example. This is a derecho that occurred last year, 19 of July, across northern Wisconsin. Again, very high probabilities for damaging straight line winds, peaking around 0.2 UTC in close agreement with what actually occurred. And then one thing that was unique about this day is we actually had a second forward propagating MCS develop over South Dakota in the early morning hours, and that was captured as well. So while most severe weather events occur across the country in a relatively short time frame, in fact, work by Harold Brooks and Kenzie Krochak showed that overwhelmingly it's within a 4-hour period. The timing guidance is very useful, potentially in cases where there's two peaks separated by several hours of relative quiet. Another case, much more recent, this is the Corn Belt or Iowa and Illinois derecho of August 10th this year, showing at least in the early morning or the early part of the convective day, probabilities that were not all that high relative to the wind reports that were received. But then as the CAM guidance came into better agreement, more of the CAM guidance was showing the potential for a higher end event, the probabilities increased, and fairly close in terms of the timing to what actually occurred. So these are certainly some challenging events. I would say that among the many challenges in forecasting severe convective storms, not only forecasting derecho occurrence, but that subset of derechos that really achieve highest end potential is a huge challenge. Now I wanted to switch and talk about another area of emphasis here within SPC. It's not something that's new per se, just increasing our focus and our emphasis on this. And that's the sub-watch scale, mesoscale convective discussions, mesobeta is how we refer to them typically, that are designed to be alerting tools after the watch is issued that really tend to hone in on where we think the greatest severe weather potential exists, and also for the higher end threat. So we're trying to identify these corridors of greater risk. This is well known within the severe weather warning process as a gap. We issue a watch with a few hours advance notice, and then the products that fill that can vary over space and time. And this is one area that Facets will certainly address. But in the interim, SPC forecasters are looking at this data. They're looking at observational trends. They're looking at CAM guidance. We can often see these corridors developing. And so our emphasis increasingly is to get that information out where folks can see it. We've gotten really good feedback from not only within the National Weather Service, but broadcast meteorologists, private sector METs, and even emergency managers who tell us that they're using RMDs as much as they are the outlooks and watches and information provided by local offices in their decision-making process. This is a fairly visible one that received a fair amount of good feedback for us. This was March 3rd, 2019. This was the day of the Beauregard, Alabama tornado, unfortunately with a substantial loss of life, 23 deaths and over 90 injuries. And this was a case where we could see parameters coming together in the vicinity of a warm front, and really put out a couple of strongly worded mesoscale discussions highlighting not only the threat for tornado genesis, but subsequent MD, relatively strong tornado genesis based on the environmental parameters. And our feedback is that it helped fine tune the message. And in the end, it's about getting people to listen and know that it's getting closer for them to be prepared to take action. And so this is something that we plan to do more in the future. Go back real quick to one more thing I wanted to say here. If you're interested more in the mesobeta scale discussions, Brian Smith, one of our mesoscale outlook forecasters, gave a talk about this very subject at the NWA meeting recently. Check that out. There's some good information there, and it just describes our tools and our philosophy going forward in that regard. I also wanted to mention that we have, over the past couple of years, issued a few relatively focused storm scale meso discussions that really are issued once we have a really high-end tornadic environment in place and very likely a confirmed tornado. This is based on a multi-year, almost decade-long work now with Rich Thompson and Brian Smith and co-authors, Doug Spieger at the WFO in Norman, other folks here at SPC and within academia. And it attempts to, through a very large data set, over 40,000 data points and growing, compare radar rotational characteristics with environmental parameters, mainly the significant tornado parameter, to try to provide quantitative estimates of tornado intensity in real time. The long-term benefit to this clearly is in the warning decision process, helping to pick impact-based warning thresholds and tags. But I also think it has benefit for first responders. Certainly, knowing once an event is underway or immediately after it's occurred, the likelihood of, say, significant structural damage, roads closed, power lines down, could enable them to respond a bit quicker and with, a higher level of urgency, given expectations for more substantial damage. So this is something that, again, has been many years in the making. And the weather and forecasting two-part articles have just today been accepted for publication. And so hopefully those will be available for early online release in the next few days. Also wanted to talk about a partnership that we have with FEMA, and it is to be more focused on predictive analytics or impacts. For FEMA and for other users, the occurrence of a tornado and their level of response is partly a function of the intensity of the event, but also what's in the path. And this is just a population density map that shows a couple of things. Number one, it shows the urban areas really well, but it also shows the increasing density as you go from west to east, from the plains through the Mississippi Valley and into the eastern U.S. Well, working here, Patrick Marsh has led the effort with Summer Erickson, who's our FEMA liaison. And we have developed what we refer to as quantitative IDSS or QIDSS. And here's an example. This is from the April 27th, 2011 tornado outbreak. And what we have done in this case is used attributes of the forecast, whether it's no tornadoes, whether it's tornadoes without SIG areas, whether it's significant tornadoes forecast, or whether it's a moderate or high risk with a significant threat. Different characteristics of the tornado likelihood is put into this model. And then it runs 10,000 simulations, essentially a Monte Carlo simulation that gives us probabilistic distributions. And so at the lower left, this is for mobile home impacts. The RBC is a reasonable best case. RWC is a reasonable worst case. And then you can see various probability thresholds for mobile homes, population, estimates of the likely number of tornadoes, hospital beds that may be in the path, electric power substations. It's really almost unlimited in terms of what you could use this information for, but it all begins with a reliable and skillful forecast. And what we found through some internal work here is that there is an exponential increase in the likelihood of an EF3 or greater tornado as you move up the distribution of SPC forecasts from tornadoes without SIG, tornadoes with SIG areas, and then into the higher probability areas with some potential for significant tornadoes. And so that's skillful information. Let's put it to use. And this is, again, in the early stages, but something that we will pursue vigorously in the years ahead. Now, this is a severe presentation, so I didn't want to go too deep into this, but it's important to note that the idea of facets of this probabilistic stream with forecaster expertise as part of the process is not just limited to severe. I think a lot of the early work has been done in the realm of severe weather, but it certainly applies to other hazards. Here at the Storm Prediction Center, one of our missions is to forecast dangerous fire weather conditions out to 8 days into the future. And so there has been some discussion in a broad sense about how facets might apply to the fire weather challenge. I think there's clearly benefits to having this more probabilistic data stream for land managers, first responders, others, people who live in the area and need to plan around the fire risk. Obviously, observational data sets, including fuels. And right now, that's a substantial challenge. Getting a nationally consistent fuels database into the process that would be important, as obviously would NWP guidance. There have been some informal discussions about the notion of a fire environments test bed, similar to what's going on within the severe weather, tropical weather, flash flood, and aviation weather hazard areas, and that's certainly being explored. I think looking ahead, we have a lot of challenges, but I think you can boil down many of them to these three areas. First is how can weather professionals best communicate this new emerging information? It's increasingly specific in space and time based on rigorous science. How do we provide this to emergency managers and other key decision makers? And how should this weather information evolve to take advantage of the new capabilities, but yet keep those simple elements of our current approach that are familiar across the public? The notion of watches and warnings might still exist, though with some modification in this world. And then how can we exploit all of this new information to develop new capabilities, but still retain the effective messages that are needed for the public to take action? Some social science work has been done that show that while there are benefits to this, there are things we have to be careful of in terms of overwhelming folks with information or packaging it in ways that doesn't lead to effective understanding. So these will be challenges, not just for us at the SPC or within the National Weather Service, but throughout the weather enterprise. And fortunately, there's a lot of work that's been done, currently being done, and the future looks exciting in terms of implementing a lot of these strategies, and it'll take a team to make that happen. And with that, I wanted to make sure I left plenty of time for questions, and so I'll certainly take any that you might have. And Nick and team, thanks again for the invitation.
Thank you. I think a lot of people got a lot out of that. If there was anybody that I know that would not get flustered over a start with no audio, it's Bill. Bill was my first MIC out of college, and you couldn't fluster the guy if he was talking. So we appreciate you being adaptable with us. We have 3 questions, all from Ted Ryan. He just, when do you expect the HREF timing data to become available to the public, and will it be sent out in a form that GFE can read for the WFOs?
Yeah, that's a good question. We'd like to get feedback on it now. It's available for NOAA.gov system users, and we are working to make it available remotely as we all continue to operate in sort of a remote world due to the COVID pandemic. Based on feedback that we would like to get from National Weather Service users, it's certainly possible down the road that it could be made available publicly. We just want to make sure that it's skillful, highly reliable. And so again, at this point, the key for us is to get the feedback. And yes, one of our goals in the hopefully nearer term would be to make it available through GFE for incorporation into local office products.
Also, and then kind of along the same lines, is there any plan to get the QLDSS forecast on a CWA or even county-based level?
At this point, the work is primarily on national, regional, state levels. The utility of it gets a little bit more questionable as you get down to really, really small scales. But nothing is off the table. It's just a matter of getting feedback, refining the process, and going from there. So I don't have a firm answer, but certainly our goal is to make it more useful with time to as many folks as could benefit from it.
Awesome. Well, thanks, Bill. Thanks for joining us. Sorry for the little technical glitch there with the software, but I'm glad we were able to get it fixed.
Yeah.
Next up, we have Cindy Elsenheimer, who's already joined us from National Weather Service Southern Region Headquarters. And this is a good topic. A lot of times, a lot of people say it's too early to tell. So when is that phrase, it's too early to tell, when won't it be the right thing to say? So messaging meteorological threats with uncertainty is what she'll be talking about. So Cindy, looks like you started the process to share your screen, so go ahead.
All right, everyone. Well, we'll just start off looking at our core partners here. These are the people we see every day or serve every day in National Weather Service forecast offices. We've done this for many years. And over the last 5 to 10 years or so, our agency has really done a tremendous job of enhancing our relationships with them and also establishing new relationships as our bonds in the communities we serve grow. Email briefings, webinars, on-site decision support, all of those services have really become standard practice now at our weather forecast offices leading up to an event or maybe in person if there's a scenario going on, maybe not so much with COVID, but when we were doing on-site support as well. And all of this information really helps them in their decision-making processes, but a lot has also really changed with how they get their information from us and what they need from us and where they can find it. Weather information continues to become more readily available on the web and on social media, and they're seeing things or hearing things possibly way ahead of weather events that we're really ready to talk about when it comes to high impact events. And these could be hours or even days ahead of that weather event. Let's take Hurricane Florence, for example. Mandatory evacuations for Florence in the state of South Carolina began September 10th, which was a Monday. This included all residents along the coast and nearly about 200 hospitals and medical facilities. Monday was almost 4 days ahead of when Florence was supposed to make landfall. And if you remember, it was supposed to make landfall in North Carolina, not even in South Carolina. So why would a decision maker inconvenience their constituents or spend a tremendous amount of money and resources when there was little certainty that this storm would even make landfall in South Carolina, since it was forecast to go to North Carolina? Well, that's easy. It's all risk management. Governor McMaster that Monday said, "We know the evacuation order I'm issuing will be inconvenient, but we're not going to gamble with the lives of the people of South Carolina, not one of them." So authorities know there's a huge trade-off between the cost and the possible benefits of making these critical decisions ahead of a disaster. So in this particular example, they're willing to cause some chaos by issuing this evacuation order, reversing the flow of interstate traffic, just to reduce the impacts of a potential disaster where the possibility for the loss of life exists. So even in a low likelihood that this would occur, the result would be a disastrously high risk on this risk assessment scale for the loss of life. Well, what happened with Florence isn't unique. It's been happening probably since we've been making weather forecasts. These decision makers have always had to balance making a decision with uncertainty in the forecast. So this is as much true as it is for tropical cyclones on the coast as it is for North Texas when it comes to a winter event, a storm, a snowstorm, or an ice storm. So what has changed though is the lead time and the amount of meteorological information that's out there from both official sources like the Weather Service and also non-official sources too. So these example tweets I have up here are not showing something irresponsible. It's not a single run of the GFS. It's not showing some deterministic output from one single model run from some Twitter troll in their mom's basement. These are actually reputable sources. And in this instance, there was good global model ensemble support for the development of a tropical system in the northern Gulf of Mexico, which ended up being Hurricane Barry last summer. So this is a big challenge for us, right? Our core partners are seeing this information and they're seeing it much earlier than we're providing them any actionable information to help them with their decision-making process. So right or wrong, we can really lose credibility in these scenarios. So one reason I think that we have difficulty fulfilling these core partner needs in that farther out medium range long-term forecasting is there really is a lack of official National Weather Service products to help tell the story for us. So in this example, in that 10 to 14 days out from an event, there's maybe a handful of products available from the Climate Prediction Center. Once we get a little bit closer in that 5 to 7 day medium range, there's a few more products. We have the National Hurricane Center forecasts. We have convective outlooks from the Storm Prediction Center. But you'll notice that the confidence in these forecasts in that medium range still remains very low. Now it's day 3, maybe before this event, and we have data and forecasts from the Weather Prediction Center that come online. We have the SPC convective outlooks that we can use. And then here, closer even still, we might enter a watch phase here that day and a half, 2 days before an event. Our confidence continues to increase, of course, and we have more high-resolution model guidance available to us. So here we are on the day of the event when we have our full suite of operational products available to assist us and our decision makers for helping them make some decisions. So of course, our confidence is the highest it's been for this event, but even with a convective event, there still may not be as much confidence as one would like for something like timing. And those details are super important, of course, for decision makers. So right here in this medium range is where we can really start to push the boundaries of science to assist our decision makers during those high impact weather threats. So for the forecasters listening, right, does this make you anxious? Does it make you a little nervous? Are you starting to think like, well, yeah, Cindy, but there's so much things, right? It's so far away. So messaging in this time range can be really uncomfortable because as meteorologists, we know that the forecast uncertainty is very significant in this time range. So we tend to want to wait until we're more confident on those really important details like timing, amounts, intensity, location. We want to wait before we start beginning to message those high impact weather threats. But this is really the time when we need to start providing that information to them rather than saying things like, well, we need to wait and see how this evolves, or I'm not sure. It's too early to tell. Let's wait a few more days till we have a little more confidence or less uncertainty. But our core partners are really going to be starting to make these decisions in this time frame, and they may be asked to make really critical decisions. So in this medium range, it would be ideal to be right, but the worst thing you can do is nothing. You got to tell them what you know when you know it. So how do we remove that desire to be right? You know, like I said before, it would be ideal on day 5 if I could tell you exactly where it was going to rain, how much, how intense, or how severe this storm would be, or this is where this tropical cyclone is going to make landfall. But the forecast uncertainty is so high at that point, it's not easy to do that, or maybe even impossible. But let's think about another example. Why is it as a forecaster, when you made a forecast for your location of a high temperature of 102 and the actual temperature ends up being 104, why does that feel better to you than, say, a thunderstorm that occurs in an area where you have a 10% chance of storms that day? That deterministic temperature forecast is actually wrong, and the probabilistic precipitation one isn't. So the first step to be able to do this is to embrace the uncertainty and the probabilities that fall out of our threat-based forecasts. I mean, we know the atmosphere is dynamic and it exhibits limited predictability, so our weather forecasts are always inherently uncertain. And our core partners are power users of those products, and they understand too that our forecasts are not perfect. But stated, like we said before, and I know Stephen mentioned in his talk too, our partners are trying to be making plans and making decisions for this stuff before there may be an official Weather Service product available to help them. So this is one of the fundamental reasons that we really need to focus on providing this information as early as possible, using probabilistic guidance to communicate the forecast uncertainty to help those users make more effective decisions on their timelines rather than ours. One of the best ways to do this is through ensemble-based probabilistic approach. So this information is out there, and as a Weather Service forecaster, it can be really challenging to find. And I'll talk more about that in a few minutes. But think about our partners. Once you know and understand what their thresholds are, it's a lot easier to tell someone that you know the probability of exceeding that threshold rather than worrying about or focusing on that single deterministic value. So in this example, imagine 3 decision makers in the Northeast, and we have a 7-day forecast for greater than 12 inches of snowfall. So imagine this decision maker further south where snowfall events are less common. Maybe their threshold is for any snowfall amounts. So this far out at 7 days, when we can see these high probabilities of 70 to 80% of exceeding 12 inches, that gives us a lot of confidence that we're going to exceed their threshold of any snowfall. Now, further north, maybe their threshold is closer to this 12-inch threshold, and the probability is lower there, but it gets us a way to communicate that uncertainty to our partners using a probabilistic approach at these locations. And our partners do understand that when the probability increases or decreases as the threat gets closer, that it means that we have more or less certainty in exceeding that threshold. So further south, they know that the probability went from 70 to 80% to maybe closer to 80 to 90% now that we're closer to the event. They know that the probability of exceeding this threshold, they have more confidence that it's going to occur. And further north, now the probability has been further reduced. So in this case, they know the probability went down. This is less likely to cross my threshold. Here, where it went up, it's more likely to cross that threshold. And it's important to not use words like possible or unlikely, and really focus more on the numbers. That helps us precisely message this much more rather than saying that something's just possible. So another way that we can do this and become more comfortable in doing this and managing that uncertainty when we're trying to message these events in the medium range is that we really need to become experts at recognizing those high impact events for our area in the deterministic model output by using conceptual models. So in order to have that confidence to message something that you see out there in the medium range, you really need to have the confidence that you will recognize that pattern when you see it. And you can also recognize trends in that pattern when it's starting to change or evolve. Maybe the threat is increasing. Maybe one of these parameters isn't there anymore, like in the example of a Southern Plains wildfire outbreak. So we really need to revisit our conceptual models and see how we can use them with ensemble model output to really give us confidence in that medium range forecast when we have to message this to our partners. Even in the national blend of models there, it's really still important to analyze that deterministic output along with the ensemble model output together to really understand how the atmosphere is evolving, how it's changing, and really gives you that more confidence to those statistical models. And it helps us identify those targets of opportunity to message to our partners, as well as any modifications we may need to make to those blended model solutions. So we need help with this, right? We need tools. This isn't something that happens overnight. This isn't something that we can do right away. We need a lot of tools to help us get here. So I'll present a few ideas of things that I think would really help us get there when it comes to messaging things more in this context. One example would be a threat-based guidance that's driven by specific Weather Service product thresholds. So in this example, it's the probability of exceeding an excessive heat warning criteria rather than focusing on that specific deterministic temperature value. And this could be useful all across the country for different things, such as freezing temperatures or even forecasting the river stages at a particular river location. And we need more products in the medium range that place this model guidance into context for us. The sounding climatology is one that comes to mind, but we really need more tools like this to help us message how anomalous an event may be that's coming up for our area. We need more calibrated and reliable probabilistic guidance too that allows us to message the range of outcomes with ease. A lot of people listening are probably thinking, well, Cindy, I still have to make my forecast and I still have to come up with that deterministic number. But if we have more graphics or more products that we can show that helps show that range or show our certainty, it becomes a lot easier to do that in addition to that deterministic forecast. So the bottom line of all of that is we really need more training. And we need training that helps us focus on these things, such as finding those targets of opportunity to deviate from the blend and teaching us how to message those meteorological threats probabilistically, because that isn't something that we have a lot of experience in, especially when many of our products still are deterministic. So regardless of all these limitations and these needs, one thing that we're trying to do in the ROC here at Southern Region is that we're trying to message uncertainty with what resources we do have. This particular year, we've really been trying to use the NBM and use the 90th and 95th percentiles to help us, especially during tropical events, come up with some sort of reasonable worst case scenario to pass along to our partners. It's something for them to plan for and be thinking about. Feedback from a lot of our partners, the state of Texas included, and probably many of y'all that are listening here, is that they would rather prepare for the worst and have it not happen than to not be ready at all. They need to make all these decisions at different timescales, and whenever those opportunities are in the forecast cycle, all they want for us to do is tell them what we know when we know it. We need to message the trends that we see as the event nears. Is probability increasing? Is it decreasing? Is the threat increasing or changing? We just have to be very transparent with all those changes in the forecast. Because in the end, just don't be afraid of being wrong, because if you're using probabilistic information, you really can't be. With that, I will take any questions.
Thanks, Cindy. Excuse me. No questions, but we did have one comment in the chat. You want to jump in after your presentation and read it and give some thoughts on it. It's a good comment, but we're going to go ahead and move on to our next talk. Abby Hudson, if she'll join us shortly. But thanks for joining us, Cindy. We really appreciated that talk.
Hi.
So next we have Abby Hudson with Texas Tech University, and we'll be talking about using ensemble sensitivity analysis to identify storm scale characteristics associated with tornado potential. So if you want to go ahead and start sharing your screen, you can go ahead and get started.
Well, thank you so much. Yeah, that title's a bit of a mouthful.
I cut the last 3 words.
That's all right. Can you see my screen? Great. Oops. Giving you a hint before I even get there. There we go. All right. If we're ready to go, so that was a great presentation, Cindy. It was very, very well articulated. I really liked it. We're going to do a bit of a change up. My work isn't necessarily on the matter of days; it's more on the matter of minutes. And but I'm excited to show you guys some of the work that ESA has been showing me on the forward flank of supercells in particular. So a little of my motivation, as you guys already know, predicting tornadoes is hard, and you guys are probably thinking, yeah, okay, Captain Obvious. But the good thing is we have good skill at predicting supercells. We know the environments that are conducive to supercells, and this is great because 75% of tornadoes that form in supercells. Meanwhile, the problem is only 25% of supercells become tornadic. And so the question is, why do some supercells produce tornadoes while others do not, even if they're in similar environments? The big thing is supercells can influence their own tornadic potential, especially through their downdrafts and the kinematics and thermodynamics associated with them. The classic supercell structure that we know of is that supercells are often characterized with a rear flank downdraft and a forward flank downdraft and their associated boundaries. These downdrafts can influence tornadogenesis through buoyancy modulation, baroclinic vorticity generation, updraft convergence. And in particular, I'm going to talk about the forward flank today, in which we see what we call the streamwise vorticity current. If for those of you out there who were listening yesterday to several of our Texas Tech Atmo groups presentations about streamwise vorticity currents, I'm going to do something similar. So as a reminder, streamwise vorticity is vorticity along the axis of vorticity is along the same direction as the wind, and it's often seen parallel to the forward flank thermodynamic boundary, which is northeast of the mesocyclone. It's baroclinic vorticity generated just behind the cold pool head, and it has been associated with the enhancement of a tornado, especially in Orff et al. 2017. And if you'll notice, look down at the bottom right of my screen, I switched that, I mirror imaged it, because I'm actually going to show you a few cross sections like this today along this orientation of, and so I want you to be familiar with that kind of look. So the goal of my work that I've been doing is to objectively identify storm scale characteristics, aka really small, associated with enhanced vertical vorticity in simulated supercells. So the simulated supercells who produce what look like a tornado, what do they have in common? And those that don't, what do they have in common? And so first I needed an ensemble of supercells. So I created one in CM1 in which I used randomly perturbed soundings from the RUC proximity sounding from the May 24th El Reno supercell sounding. If you're unfamiliar with it, I can show you later at some point, but it's a powerful sounding. It produces anything that spins, really. And so that helped me form this ensemble. On the left here, I have a time series of reflectivity averaged across all ensemble members. So each image moves forward in time. 5 minutes after the perturbations were introduced, all of my members are producing a supercell, and it's pretty similar. But as the reflectivity contours get smoother, that means that my ensemble members are gaining some spread in the shape and the look of their supercells. But all in all, they are all producing supercells, which is great. But I also wanted to make sure I had spread. And so while there is thermodynamic spread in the forward flank downdraft, both in potential temperature and equivalent potential temperature, I wanted to make sure I had spread in which ones were produced tornadoes and which ones weren't. And here's this busy plot is another way to look at the spread in my ensemble. Each row is a different ensemble member. And as you move across, you're moving forward in time. And each black bar represents a tornado-like vortex, which I defined for you here. And then the red bar is a tornado-like vortex that has a vertical vorticity of 0.2 per second at that instance. You see different vertical vorticity maximums at different times. You see some members, like member 4 here, that don't produce a TLV. And you see some, like member 30 here, that produce a lot of TLVs for quite a while. So the question is, how do I now objectively analyze an ensemble such as this? Well, I have the honor of introducing to you ensemble sensitivity analysis, or ESA for short. I know the presentation after me by Austin Coleman is going to give you a much better explanation of this technique. But just to run through, it's a statistical technique that finds a linear relationship between the response variable of interest, J, and the initial state of the storm at an earlier time, X. J can be things like vertical vorticity, and X can be things like temperature 10 minutes before that vertical vorticity measurement happens. Easily enough, you can calculate this using the statistics of the ensemble. You do the covariance of the response variable over the initial state variable divided by the variance, and you get what we call sensitivity. So graphical representation of this technique is what you can see down here in the bottom left. You see a scatter plot data that represents one particular grid point in the ensemble. Each scatter point represents an ensemble member, and on the x-axis we have our state variable, like temperature, And on the y-axis, you have your response variable, like vertical vorticity. And the linear regression, this black line, is our sensitivity. We get a numerical idea of how much J responds to X. I'm going to show you a few plots now in which I show like a horizontal look at all of these sensitivity values, and these positive sensitivity is going to be in red, and negative sensitivity or a negative slope is going to be in blue. So here are going into my results a little bit. I am looking at the response variable of vertical vorticity at 135 minutes into the ensemble. Some supercells are producing tornadoes or TLVs, some aren't. So, and this sensitivity here is showing the sensitivity of that vertical vorticity to density potential temperature 10 to 15 minutes before that response time. In the forward flank, what I want to point out to you is this dipole here, where you see a strong negative sensitivity next to a strong positive. This is a positional sensitivity. And I'm going to show you why. And the plots here on the right, you see the 10 strongest members, their average density potential temperature, so averaged across those 10 strongest members. On the right, you see them averaged across the 10 weakest members. And you see in that contour there that's outlined by the red sensitivity, that's a big difference between the two. The strongest members are a lot warmer. So what is this? Well, a good way to figure out what this is to look into the vertical. And so we take a cross section of that sensitivity, and we see that we have a red versus a blue, and that dipole again, and it's tilted upward and to the west. And so what this is showing us is the sensitivity that the strongest members have a cold pool that is further to the east than the weaker members that have a forward flank cold pool that is further to the west. For reference, the 0 here is the center of my mesocyclone. And so you see that weaker members have it to the northeast and stronger members have it to the east-northeast. So why might the position of this forward flank cold pool affect vertical vorticity? Actually through streamwise vorticity, bringing it all back. So changing the location of the cold pool changes the location of the area of maximum streamwise vorticity in the horizontal. So what you see here is that in our strongest members, this is a color-filled plot of streamwise vorticity. In our strongest members, not only is the streamwise vorticity further to the east, but it's also closer to the ground. In the weakest members, you see it further to the west and above the surface a little bit. What's happening here is that the maximum of streamwise vorticity happens to be located underneath the tilted mesocyclone. So in supercells, we have that mesocyclone that's tilted, and in this particular simulation, it's tilted slightly to the north. And with that, the mesocyclone located above this region, we get upward motion underneath it. And that upward motion is taking our streamwise vorticity current and taking it above the surface and stretching it in the vertical. And that's what I'm highlighting for you here. You can actually see that vertical motion. You can see the impact of the mesocyclone that is actually affecting our streamwise vorticity. So in my crude drawing that I have for you here, what I'm finding out is that the weakest members that have the cold pools located further to the west, so northeast of the meso, but not as far east as the stronger members, they're getting influenced by that tilted mesocyclone. And the streamwise vorticity current, which I'm drawing for you in that red line here, gets tilted up and away from the surface and isn't therefore close to the surface where a tornado would be to be tilted sharply into the vertical and thus enhance that tornado. Now, when in the stronger members, when that streamwise vorticity current is located further to the east, you actually get to see it stay close to the surface, provide a large amount of streamwise vorticity to therefore be sharply tilted upward underneath the low-level mesocyclone, and therefore possibly enhance the tornado. These are just some of my results from the ensemble sensitivity analysis of this highly idealized supercell, but I'm getting some interesting results. So that's all I have.
Thanks, Abby. That's really interesting stuff. I like how you showed the maps there and kind of we were able to visualize that pretty well there at the end. I think time and time again from different presentations from you guys at Texas Tech is the cold pool has a high correlation with tornadogenesis and the position of that cold pool. So that's really, really cool stuff. Let's see. We had one other quick question: is have you tried sensitivity to streamwise vorticity itself?
Yes. So that's actually what this plot is. It looked very similar to the temperature one, so that's understandable. But yeah, and so the supercell, the ensemble of supercells that I'm having, they actually all produce a great amount of streamwise vorticity, especially in the forward flank. So I'm seeing more of a sensitivity to the position of it than the actual magnitude of the streamwise vorticity when it comes to a response variable like vertical vorticity at the lowest level. And so, yeah, I am doing sensitivity to streamwise vorticity both in the vertical and the horizontal.
Awesome. Great talk. Thank you so much. It looks like our next speaker has arrived, another student from Texas Tech University, Austin Coleman. Presentation will be improving forecasts of high impact weather through sensitivity-based ensemble subsetting. So looking forward to this one as well. So if you want to go ahead and unmute yourself and start sharing your screen.
Guess I unmute first.
There you go.
Yeah. And there we go. Okay. Should be able to hopefully see my screen. Awesome. Thank you so much. So yeah, we're zooming back out now time-wise and now looking at improving forecasts more on the day 1 and day 2 scale. But first things first, why would we want to use a tool like ensemble subsetting to improve these forecasts to begin with? So we know in recent years we've seen this shift from the single solution forecast of severe convective weather to mini forecast solutions known as an ensemble system. These are great for forecasters, allow us to characterize this uncertainty, and shift to this probabilistic framework. But unfortunately, we can only run these large, sophisticated ensemble systems about once or twice a day due to computational expense, which can leave up to 12 hours of potentially critical observations idle in between those forecast launches. And so our goal is simple. We want to improve these ensemble forecasts of severe weather by confronting the ensemble with those unused observations without the need to apply these additionally computationally intensive data assimilation cycles in the process. And so we're doing this with a tool called ensemble subsetting based on insights gained from ensemble sensitivity analysis. So what is ensemble sensitivity? Well, Abby already gave us a really awesome description of that. So I'll just do a brief recap here. So ESA essentially describes how some chosen high impact forecast feature known as a response function relates back to the early atmospheric state. And so this is done through a simple linear regression line where the slope of the linear regression between your response and sensitivity variable becomes your sensitivity. And so this is the slope of this line is calculated for each grid point within a model domain, producing a sensitivity field like the one seen on the right. And this is where ESA becomes a really powerful diagnostic tool because we're seeing which early changes to the 300 millibar height field are going to affect the extent of high updraft helicity coverage in this area here shown in green, which is known as the response box. And so it's taking these relationships that we already understand dynamically, but quantifying them within the context of the ensemble itself. And so knowing which early atmospheric features are most relevant, we can now combine this field with early observational analyses to identify which ensemble members have the best handle on those really critical sensitive regions. And so this was initially attempted at synoptic scales where Brian Ansell applied this technique to try to improve forecasts of sea level pressure for landfalling cyclones off the West Coast. And it was found for a variety of different subsetting configurations that you could get statistically significant reductions in error with these forecasts. So really promising results at synoptic scales. And so the natural progression was then to see if we could apply this to convective scale forecasts, where of course we know, we get additional challenges given the dynamic nature of convection. And so we set up an idealized experiment where we randomly selected an ensemble member to serve as truth without replacement, and then wanted to answer two primary questions. First off, can these subsets outperform the full ensemble forecast? And if so, which combination of subset parameters gives us the most benefit to our convective forecast? So in this case, we're trying to improve forecasts of mid-level updraft helicity. And so with that in mind, we applied this large permutation experiment to 16 cases from May 2016. And this is all within the Texas Tech ensemble framework. So first thing we wanted to know was whether the subsets could improve the forecast consistently over the full ensemble. And what we found was pretty encouraging. So over 70% of the subset configurations were able to reduce error for UH forecasts over the full ensemble for all 16 cases. So the vast majority of these subsets were really consistently improving the forecast. If we look at what those improvements look like, we find that most of the subsets are actually reducing error by at least 50%. Compared to the original full ensemble, and those reductions in error are statistically significant for the most part. So both substantial and consistent improvements in the forecast. Another really interesting outcome from this experiment was, so we tried varying the subset size as well, from 1 member out to 40 members. The original Tech ensemble is 42 members. And we found that 1-member subsets actually tend to provide the most benefit to the forecast in these idealized scenarios. And this suggests that the subsetting technique is really good at picking out the best possible ensemble solution first, and then incorporating subsequently less skillful members as you increase the subset size. And so this was all really encouraging, and we wanted to see whether these results translated to a practical framework. And so we applied the same permutation experiment to forecasts of UH, where we verified with local storm reports and practically perfect probs, and also to reflectivity, where we verified with reflectivity radar data. And we found that no, the nature of the idealized results does not translate to this real-world framework. And interestingly as well, the reflectivity subsets outperform the UH subsets for the most part. And so given this kind of conundrum, we decided that maybe trying to verify these UH forecasts with storm reports, because we know that a UH swath does not guarantee a storm report, is maybe trying to compare apples and oranges. And so that could be potentially masking the utility of the technique. Given this discrepancy in the nature of the objective results, maybe the best way to evaluate tools like this is to ask the end users, the people who will be using the product. And so we've been lucky enough to bring the subsetting technique to the hazardous weather test bed the past few years. So as Bill kind of talked about, the HWT is this month-long program in Norman every year, where each week a new group of forecasters and researchers are chosen to evaluate these new products. So we brought a pretty simple experiment to the test bed in 2018 with the TTU ensemble, where we had 3 preset responses, 6-hour UH max, reflectivity coverage, and UH coverage. And each day the participants would look at the TTU ensemble probs and pick a forecast problem of the day to design the response box and response time around. And then subsets will be calculated. And then the next day, the forecasters would compare the full ensemble and subset probabilities to local storm reports and practically perfect to decide which forecast fared better. And the results from that first year within the TTU framework were really encouraging. We found that the majority of participants said that the subset outperformed the full ensemble in the response box. And also comforting to see was that while the subsets weren't always outperforming the full ensemble, they very rarely degraded the forecast. So just to walk you through, kind of give you more context on what that looks like, here's a success case from May 1st, 2018, where we have the full ensemble probs of 6-hour UH exceeding 25 meters squared per second squared in the top left, subset probs in the right. And then most importantly here, we have the difference between the two. So the warmer colors indicate that the subset is increasing probabilities over the full ensemble. And you can see here that well ahead of the event, we're seeing the strongest increases in the northwest side of the response box, which correspond really well with the corridor where the most active weather actually occurred. So we're trying to kind of get the subsets to nudge the probabilities in the right direction. Of course, we can't always have cases that work out this well. So 9 days later, we had a pretty spectacular failure case where the forecasters picked this uncertain signal in southeast Colorado. The subset was really gunning for something to happen here. And not only did we not get any storm reports in this area, I don't even think there was any convection here on radar at all. So not a great day. But for the most part, we found pretty encouraging results with the technique during that year. So we brought back the subsets to the 2019 test bed, where this time we spiced things up a little bit by applying it to the 58-member selection from the Community Leverage Unified Ensemble. So the clue is the super ensemble, where a bunch of different modeling divisions contribute various CAM ensembles. And this makes it kind of tricky because now we're applying it to a multi-model ensemble, which has some limitations. And so to mitigate these, we calculated the sensitivities within the TTU framework and then applied them to the clue ensemble afterwards. The results for this year weren't quite as exciting. For the most part, the subset skill and the full ensemble fared about the same. But we did see some unexpected, really interesting results from looking at which clue members were picked each time. So here's a histogram of how often different clue ensembles were chosen within the subset. You can see that clearly the HURI is most favored by the subset throughout the experiment. But really interestingly, there wasn't a single instance where any of the FV3 members were chosen for the subset throughout that month-long experiment. And it kind of suggests that maybe there are these system relative biases between, definitely between the TTU ensemble early forecast state and the FV3 early forecast state, but perhaps even between ensembles of different dynamic cores, atmospheric states. And then, of course, we brought the subsetting back for the 2020 at HWT, but it was a little bit of a different fashion there. This time we applied it to the 18-member time-lagged HURI ensemble with 9 members initialized at 18Z and 9 initialized at 0. And this was really exciting because time lagging does seem to be this really have a lot of potential in terms of an efficient and really good way to design an ensemble. And so we wanted to see here if the subset was able to, both pick good members, but also, would it actually choose members from the 18Z initialization, or would it mostly focus on the 0Z? Is it valid to apply this technique to a time-lagged ensemble? In addition to the subsets, we also provided a best member product this year to evaluate, given that the idealized experiment suggested that one-member subsets might provide the most benefit. So like many things in 2020, the best member guidance was not great. The majority of participants responded that the best member detracted from overall forecast guidance, and there's quite a few examples of this. But on the bright side, we did find that the subset actually chose the 18Z members, interestingly enough, over half of the time. Which does suggest that, if you apply subsetting to a time-lagged ensemble, maybe those members are on the same playing field and you're not just going to get 0Z members each time. And so while we didn't have a whole lot of success cases from the HURI this year, I did want to go over this success case from the TTU this past spring. So we were running the TTU subsetting in tandem with the HURI subsetting. And I think this is a really interesting case. This is from May 7th of this year, and you can see that the full ensemble UH probes are focused in on this area in the Red River. But if you look at the subset, clearly it's shifting the probabilities further southwest and strengthening them as well. But I think what's really interesting here is if we look at the full paintball on the bottom row, you can see that the subset is also picking out, honing in on this kind of convective mode, favoring these isolated, long-lived cyclic supercells. And as you can see, that's pretty much exactly what happened. We had this supercell that initiated in West Texas and produced a large hail for the majority of its life cycle. And if you want some meteorological eye candy, Alex, who we heard from yesterday, took this really awesome time lapse of the supercell coming off the cap rock. But more importantly, this was also Gunner's first supercell. So this is Vicente's dog, who we heard from earlier today. So we were a little bit preoccupied with this over the storm. But anyway, long story short, we did find that the sensitivity-based subsetting technique does have this fundamental capability to improve ensemble forecasts of hazardous weather. But optimizing the technique in the real world is very challenging, especially given this as a test module to various southern region forecast offices for operational evaluation and feedback. So stay tuned for that. Hopefully this spring we'll have some sort of virtual NWS road trip idea started. But more broadly, I think this is a really good ode to data mining techniques in general. We have these large, sophisticated data sets coming out daily or even sub-daily, and I think we can really get a lot out of them for minimal computational expense. As we move forward, I think it'll be really important to make sure these tools are interactive and integrate forecaster knowledge, and hopefully we can continue building tools around the needs of forecasters. So thanks so much, and I'll take any questions.
Awesome stuff. Doesn't look like we have any questions, but I really enjoyed that presentation. And as always, as an operational forecaster, I look forward to y'all bringing that to the field and seeing what we can do with it. So really cool stuff there. We thank you for presenting with us this year.
Thanks for having me.
Next up, we have Russell Manser, another student with Texas Tech University. His talk is on the verification of convection allowing initial condition ensemble modeling systems with the WRF ARW. So Russell, if you want to go ahead and start sharing your screen, we'll let you take it over.
Hazards probabilistically, but typically in a qualitative way. And this is often based on deterministic convection allowing model guidance and sometimes some ensemble probabilities as well as analyses and observations. And so they're combining all of these things to produce qualitative probabilities such as those issued by SPC outlooks for tornadoes, hail, and wind. So ensembles can provide quantitative probabilistic forecasts of these convective hazards, but there's a couple of problems with them. They're computationally expensive, and we don't know what the best configuration is for convection allowing models. So some recent work looked at this problem, Schwartz et al. 2020, and they looked at 5 initial condition ensembles for convection allowing models. And a few of the main results that they found were that high quality IC centers are important for forecast accuracy and discrimination. Initial conditions with random noise and mixed physics or dynamics have more reliable forecasts. And then continuously cycling ENKFs may not be optimal for CAM ensembles. So this study is very similar to Schwartz et al. 2020. And I will return to these results at the end and compare my results with theirs. So at Texas Tech, we run the TT-WRF real-time ensemble modeling system and data assimilation system. And so we run a ENKF, and some of you may be familiar with the output of that. So this is an example of that. It's a probability of precipitation of 0.25 inches or greater from the ensemble. And what we want to know is there a better initial condition strategy than the current ENKF that we're using? Is there a computationally cheaper alternative? And can we balance computational expense with improved verification? So next I'll talk about my methods to answer these questions. So I'm using the Weather Research and Forecasting Advanced Research WRF version 351. The computational domains are on the left here, and these are the same domains that are used for the real-time system. So the outer domain covers CONUS and adjacent regions, and it has 12-kilometer grid spacing with parameterized convection. And then the inner domain has 4-kilometer grid spacing, and it allows explicit convection. And so the rest of the configuration options are on the right here in this table. We're going to hold these configuration options constant while we initialize all of these ensembles that we're going to look at. So we're going to initialize ensembles with 42 members, which is the same number of members as the real-time system. Initialize forecasts at 0 and 12 UTC for 48 hours. And we're going to look at a period of late spring to early summer of 2016. So the ensemble configurations that I'm looking at include the following. So the initial condition strategy is on the left and the description of it is on the right. I'll look at downscaling global ensemble forecast system members to the 12-kilometer grid. The GFS perturbed ensemble is adding random correlated noise to GFS initial conditions with WARPFAR. The ENKF is the current system that we use, so we generate continuously cycled members with the data assimilation and research testbed software. And the recentered ENKF is taking those ENKF members, subtracting out perturbations from the mean, and then adding those perturbations to GFS initial conditions, and then running a forecast from those. And so these first two strategies are the cheap alternatives. So all we need to do is grab the initial conditions, process them a little bit, and then run the ensemble. Well, these last two strategies are expensive. We need to run in-house data assimilation in order to get the initial conditions for these. So I'm going to go look at probabilistic verification of these forecasts today for precipitation and updraft helicity. I derive probabilities for the forecast using the neighborhood maximum ensemble probability method with a searching length of 64 kilometers. For precipitation, I got observations from the stage 4 data set, and I derived probabilities using a neighborhood probabilities method, and looked at thresholds of 0.1, 0.25, 0.5, and 1.0 inches. For maximum updraft helicity, I got observations from SPC storm reports, and I used the practically perfect probabilities method to derive probabilities, and I looked at thresholds of 25, 40, and 100 meters squared per second squared. I used a smoothing parameter of 2 in the equation for the practically perfect probabilities. To verify these forecasts, I'll look at 3 different metrics. For accuracy, I use fraction skill score, which is the fraction of MSE to a reference MSE. And that goes from 0 to 1, where 1 is a perfect forecast and 0 has no skill. Reliability diagrams assess the calibration of these probabilistic forecasts. We want to see our forecasts along the 1-to-1 line, but often that's not going to be the case, and I'll explain more once I get into the results, what those other cases look like. And then for discrimination, we'll look at area under the receiver operating characteristic curve, or ROC curve. For AUC of 0.5, that indicates that the forecast has no skill, and then perfect forecasts would have an AUC of 1. So now I'll move into some results. So I'm going to first explain what these plots look like, as I'll show multiple plots that are very similar to this. So on the y-axis, we have the forecast metric, or the, verification metric. In this case, it's fraction skill score. And note that each of the y scales changes on each of the plots. On the x-axis is hourly forecast lead time. And then at the top of the plot is the statistical significance markers with a confidence of 95%. So it's comparing any 2 pairs of ensembles, where blue is the downscale GEFS, yellow is GFS perturbed, green is ENKF, and orange is recentered ENKF. And so what we want to see for a good ensemble is a higher density of statistical significance markers at the top of the plot. Okay, so what these 4 plots are showing us for precipitation at the 4 thresholds is that over the first 1 to 12 hours, ENKF tends to have more accurate forecasts. And then 12 to 24 hours, recentered ENKF tends to have more accurate forecasts. And past 24 hours, downscale GEFS tends to be the best. Now we're looking at reliability. So on the y-axis is observed relative frequency, and on the x-axis is the binned forecast probability in increments of 10%, centered on 5%. And the 1-to-1 lines right here, so all of our ensembles are to the right of that line, which means that they're overconfident in their forecasts. However, GFS perturbed is the closest to reliable among all of these ensemble systems for all of these thresholds for the most part. And ENKF tends to be the furthest away from it. So it is the most overconfident and least reliable. And recentered ENKF and downscale GEFS, the orange and blue lines, tend to be pretty similar in performance. For area under the curve, we see pretty similar performance between all ensembles except for ENKF, which tends to do the worst. We'll also notice that as we go up in threshold, the flow-dependent ensembles tend to perform better in those earlier lead times. We'll see ENKF and downscale GEFs with higher densities of statistical significance markers in those earlier lead times with higher thresholds. Next, we're going to look at updraft helicity, and again, those three metrics of FSIU. And so this indicates that none of the ensembles have skill in forecasting updraft helicity. We might be able to pick out a pattern here for 25 meters squared per second squared, where downscale GEFs tends to do better in the first 24 hours, and GFS perturb better past 24 hours. But otherwise, the data is pretty noisy for these higher thresholds. When we look at reliability, we see a similar pattern where all of the ensembles are very overconfident in their forecasts since they're all to the right of that one-to-one line at the lowest threshold. And then as we go up in threshold, there's a lack of data in these higher probability bins. So the ensembles aren't even forecasting at those higher probabilities. For area under the curve, it's a little more promising. We see that at 25 meters squared per second squared, all of the ensembles tend to have some skill past 12 hours, but ENKF tends to be the worst, and GFS perturb tends to be the best. And then as we go up in threshold, again, the data is getting pretty noisy, and it's hard to discern a clear pattern from that. So to summarize and conclude, going back to the Schwartz study, we see very similar results as they got. So we see high quality initial condition centers are important for accurate and discriminate forecasts. We see that with GFS perturbed and recentered ENKF having good forecasts. ICs with random noise tend to produce more reliable forecasts. So that would be GFS perturbed having more reliable forecasts. And continuously cycling ENKFs may not be optimal for CAM ensembles at this time. And we see that with ENKF having poor verification. So we got these similar results despite differences in methods. Here we used NMEPS, whereas they used neighborhood ensemble probabilities. Here we had 42 members, whereas they had 10. And here we looked at the South Central US while they looked at all of CONUS. And there's some other differences as well, but we still got similar results. So in conclusion, the current ENKF configuration provides relatively little benefit. So I suggest that we move to GFS perturbed because it has generally similar or higher quality forecasts over ENKF. It's less computationally expensive and is less complex to run. So I'd like to improve the GFS perturbed forecast by tweaking a few things, variance magnitudes, the perturbation scale length, and also trying the 6-hour GFS forecast initial conditions versus an analysis. And then I'd also like to inflate the recentered ENKF and downscale GEFs observations. I saw that in upper air and surface verification that these tended to be pretty under-dispersive. So I'd like to try to flatten out their rank histograms, which I didn't show here, but that might improve those forecasts as well. So we'll go back to conclusions, and I'd be happy to take questions.
Looks like we had no questions come in, but just want to thank you for joining us this year. Very interesting presentation, and yeah, just thank you for joining us this year. Glad you're able to be a part of this conference.
Thank you.
Looks like our next presenter is already in the Google Meet. Chad Gravel with the National Weather Service Southern Region Headquarters. His presentation is on using NSSL's experimental Warn-On forecast system to message uncertainty in high-impact convective events. So Chad, looks like you're ready to go. So go on.
Hey, thanks everyone. All right. So, by the way, I'm using the NWS sanctioned slide deck format. I just want to be clear on that because that's very important. Doesn't seem like a lot of you have followed these directions, but you know, so you're going to see these great slides. Okay, but it's the content that matters, right? So today I'm going to be talking about using NSSL's experimental Warn-On forecast system for weather service operations. And I'm going to kind of walk you through a timeline of how this started and where we're going to end up going. Okay. So just a brief little blurb about the Warn-On Forecast system. It's a convection allowing model ensemble. It runs every 30 minutes. Runs at the top of the hour, go out to 6 hours, and bottom of the hour runs only go out 3 hours. Outputs at 5-minute temporal resolution. 3-kilometer grid spacing covering a 900 by 900 domain, like is shown there to the left. The HURI is the background field. The data simulation, like has been talked about today, is the Kalman filter cycling using reflectivity, radial velocity, GO16 data, surface obs, and that data is assimilated every 15 minutes. It's an 18 forecast member ensemble system, and it's run quasi-operational from May to August. We'll talk more about that later. So the distinction between the Warn-On Forecast system and other convection allowing model ensembles like the HRAF and the HURI really lies in the temporal and spatial scales of the probabilistic forecast guidance. So if you think about things like the HRAF, it's really trying to answer questions, where and when will storms start and end? What are the general storm risks? How widespread? And it's really, really great guidance for like SPC outlooks. But the Warn-On Forecast system is more on the lines of individual storm attributes. So where will this storm track? How fast will it move? And how will its risks evolve with time? And it really wants to try to bridge the gap between the tornado watch phase and the tornado warning phase. And you can see that here in the middle. So we're looking at mid-level 2 to 5 kilometer updraft helicity exceeding 60 meters squared per second squared, and where the threat is for basically rotating storms. So one of the goals that we've had in Southern Region Science Division, starting in FY19 for a portion of it, a bigger portion of FY20, has been to introduce Warn-On Forecast output to a wider forecast base. So while the Warn-On Forecast team has had forecasters evaluate the products, both in the hazardous weather testbed and remotely, there just hasn't been a really large net cast, before this 2019-2020 time period. The Norman Forecast Office, which is some of their forecasters are seen here, working with the Warn-On Forecast team and trying to really see how you can apply some of this guidance. They have this unique situation of being co-located in the same building. But we're not all as lucky as the Norman Forecast Office, or unlucky, I guess you could say. So we just wanted to basically cast a wider net, okay? And this output was from May of 2017, and they were trying to use this in real time, and the wording that they used in a significant weather advisory was there was a high probability that tornado warnings would be issued based on this guidance. So that's the kind of bridge that the Warn-On Forecast team had to some operational weather service forecasters. So one of the things that I wanted to do is I was like, well, let's just basically look at tornado initially. So what I ended up doing was keying in on a few fields, and the ones that I really keyed in on were the 0 to 2 kilometer updraft helicity fields. So here is a 90th percentile value. And what it really does is it really catches your eye on where you need to be worried about and what storms have the best chance of low level rotation. And applying some research by Trepp et al. In 2005, which basically found that 0 to 2 kilometer updraft helicity was the best proxy for tornado occurrence based on some of these storm scale modeling fields. So knowing that, learning that, when there was this quasi-operational period in May, late April, May of 2019, one of the things I did was I was looking at this output in real time by myself, you know, in a silo. And when I found some interesting things, I would share them with the affected science and operations officers, basically. So here's one of those cases. And another side thing I wanted to do is I wanted to really see where Warn on Forecast output fit with facets. Because for those of you in the Weather Service, we've heard about facets for a while now, 5-6 years, and it's been very theoretical, you know, big picture. And I wanted to really try to dive in and see, one, how facet or how Warn on Forecast could fit in the facets, you know, and then other tools that we had, how they could fit in the facets as well. So this is basically a case study of one of those. And one of the things that I learned was facets is really a mindset, right? It's honestly a way of operational meteorology. It's a way of living, right? And for those of you who know Friends, it's really a state of total awareness. And I want you to think about that, this Unagi approach to facets as we're going through this. So the case we're going to look at is the high risk bust from 2019, May 20, 2019. I use bust in quotes, by the way. We're going to really focus on the Tulsa CWA. So part of their CWA was in a mod risk. Most of it was in an enhanced risk. So that kind of sets the stage. 12Z HREF calibrated probability of tornado guidance valued at 4C did show a higher threat for tornadoes in the Tulsa CWA. Okay, and there was a tornado watch that was issued around 22Z or shortly after that covered half of Tulsa CWA, or most of it, I guess, and then Springfield and Little Rocks. You can see at the time of the issuance, there's this QLCS type system that grew upscale very, very quickly from convection out west. Here was the radar at 1Z. And the reason why I'm showing you this is because now we're going to look at a Warn on Forecast run that had this radar data assimilated into it. Okay. So again, QLCS, relatively weak convection, showery type convection ahead. This convection was moving to the north. The QLCS was moving to the east. Okay. And then you can see that here's the initialization. It simulated things pretty well. It looks reasonable. So now here's about a 2.5 hour run of it. Again, we're looking at 0 to 2 kilometer updraft helicity. And one of the things you'll see is basically anywhere along the QLCS has basically a high probability of low level rotation. So while that's useful, it's really not super useful because the forecaster has to be almost continuously aware that there's a threat. You know, that's very exhaustive for the forecaster, okay? So let's move ahead a little. So now we're gonna look at 0130 or so, and we're gonna look at radar data, but we're also gonna add now UW SIMS, SS SIMS, so we're looking at Wisconsin SIMS, ProbTor output, which will become operational very shortly in MRMS version 12. But the storm I really want you to focus on is this one down here to the south where I have ProbTor 12% labeled. And what you're going to see is as we put this in motion over the next 45, 50 minutes, that storm is actually increased quite a bit in strength. You can see that the low level rotation, you know, from the Tulsa radar, or like mid-level probably here at this beam height, it has strengthened over this time. And prob tor has increased to basically 81%. Okay, so now let's take a look at the next run of the Warn on Forecast guidance. And again, this is the initialization radar. Here's that supercell that we were worried about. And you can see where our box is basically here, our radar box. And you can see it's pretty reasonable. And now this is what ends up happening. You can see that that supercell now is pretty well sampled by the Warn on Forecast system. There's a high probability of low-level rotation. And the interesting thing about this run is when that supercell ends up basically merging with that line, look what happens to the low-level rotation. It increases dramatically. And this is useful information to the forecaster, because now we can be uber sensitive about that couple county area and really, really, watch that supercell and watch trends in that supercell and how it merges with that convective line. So this is what ends up happening in this case. When that cell merges with the convective line, tornado warning is issued, and then ends up being a tornado emergency. And that Warn on Forecast guidance was available to the forecaster about 45 minutes before this happened. And you can see the bottom images are just a zoomed in of that. So you can see that. And then the one more interesting thing, and Bill Bunting talked about this in his keynote at 1 o'clock Central Time, is that now there's tools and there's research available to us in real time to actually give you a proxy, an experimental tornado wind speed of what that tornado is doing in real time. So here, and this is based on research by Brian Smith. They have papers coming out very shortly. I think, Bill said they were approved today. From Ariel Cohen. And then this web interface is by Tomer Berg. Weather Service forecasters, just so you know, the Storm Prediction Center has an in-house version of this that's very probabilistic. So what you'll end up seeing here is when it's asked for these radar these radar observations as well as environmental observations, etc. What ends up happening is something that's very deterministic. So simulated tornado speed of 133 miles per hour. Now that output is very probabilistic. We're working with the Storm Prediction Center to get that web page, get you access to that web page. But this is what you can do. So you put all the parameters in. You can do this very quickly in about 30, 60 seconds, get something spit out. And what ended up happening after the storm survey is an EF2 tornado. So that 133 mile per hour preliminary estimate of the strength in real time was a pretty good estimate. So that's what I'm talking about, using Warn on Forecast with all these tools. So that was my little case study. So where are we going here? So I have a couple more slides. So more recently, in FY20, so in FY21, one of the questions that I wanted asked is, during these operational periods, how can we really extend the Norman experience to a wider southern region base? So how can we open this up to more forecast offices? So one of the things we ended up doing is we created a Google chat room. And that Google chat room in real time provided people a central place for conversation and collaboration, a persistent topic-based communication forum. And what we ended up learning over this month is this Google chat room allowed all of these things. So it allowed for deep R2O, O2R collaboration. It allowed for sharing of Warn on Forecast logistical information, where each run would be on each day. And then it also allowed for potential case studies to be shared with the Warn on Forecast team. Here was one of those the next morning. So a high wind warning was issued based on very strong anvil winds in the Norman, Oklahoma City area. So there was a heat burst, and the Warn on Forecast guidance really provided great information on giving that forecaster confidence to issue this high wind time while events were ongoing, but also shortly after as well. And then the last thing that we have done is we've created a Continental West Warn-On forecast team. So that includes 9 WFOs from Oklahoma in West and in North Texas. And this group is made up of entirely Weather Service forecasters, so it's non-management. So we have SUs that are co-facilitators, along with myself and along with Katie Wilson, who is the Warn-On forecast team lead. But we're going to ask them, and we're going to investigate model performance and mesoscale environment, value added to the forecast decision process, and things like that. And we've only had a couple meetings, but you can see how we're going from my, very crude silo case study, is this a valuable approach, to this more, this wider forecast base. So in the end, I just wanted to show how we're really strengthening R2O2R in Southern region, with many of the forecast offices that are on this in this conference as well. So with that, I'll take any questions if there are time, and there aren't any because I know I'm over. So thank you.
Thanks, Chad. I think very good information that I think a lot of us will get useful time out of. There are a couple of questions, but since we only have a 15-minute break,
Yep.
do you mind hopping into the chat and answering those? They're really good questions that I think people need to know the answer to. But in the interest of our 15-minute break, let's go ahead and break. And if you don't mind answering those
That'll
in
be
chat.
fine.
Cool. Well, we'll take a 15-minute break. We'll be back at 3 o'clock for our last session.
That's good. I see your white spot with the TXWX in it. Oh, there you are. Well, this is promising. Let me make sure I can share my screen once again for a moment. And that looks promising too. Looks good. Well, I guess I could do that. Yeah, I'll do that and go into presentation mode on it. Okay. Okay. Well, with my screen in slide presentation mode, I don't have a mute button anymore, so I'll just stay quiet for a while.
All right, welcome back. It's 3 o'clock. We're going to go ahead and get started on our. We're going to go ahead and get started on our last session, session 8 of the conference. We have Dr. Nielsen Gammon with Texas A&M back with us. Looks like everything is running smoothly today. Looking forward to this presentation titled "The Worst Case Scenario." So why don't you go ahead and take it and run with it, Dr. Nielsen Gammon.
Okay, thanks, Nick. And hopefully I won't run away from the presentation like I did yesterday. So this is about Hurricane Harvey, and it's not about what Hurricane Harvey did as far as we know, but it's about what Hurricane Harvey might have done. So these are two analyses of the total precipitation for the event, just in case you've forgotten that we had a major hurricane stall and produce 30 inches of rain over a widespread portion of southeast Texas just a few years ago. The highest point totals at any gauges were a couple of gauges in the Port Arthur area that each recorded more than 60 inches. So far, I've seen two different narratives for greatest amount of precip in this event. One is the Port Arthur observations, and another is an observation from Baytown that was when the Houston Galveston office reported that the record had been broken. But of course, it was still raining, and also that particular gauge wasn't. But bad news for extreme rainfall fans, those reports are probably not correct. I've been looking recently at a comparison of those gauge totals with gauges that are nearby, and you'd expect that in any given hour, one gauge would be similar to the average of the gauges on either side of it. Since it's the wettest gauge, it might be more than 50% of the time, but in these two particular gauges, they went out 81 or 84% of the time, which is an unlikely number, and the precip amounts are biased, at least apparently, by 37 and 59% respectively. So we're digging into that a little more detail, but Harvey may not have been quite as wet as thought in terms of point totals. Of course, it still wins the grand prize for rainfall over a given area. This is a composite of 18 different tables. Each table shows precipitation amount averaged over a certain area size, 1,000 square miles in the upper left, 50,000 square miles in the lower right, and different durations from 48 hours to 120 hours. Each storm gets a different color. They're ranked, and Harvey, you notice, is number one in every single category. The color scheme is arbitrary, but the blues and greens correspond to West Coast storms, and the reds and oranges correspond to Gulf and East Coast storms. So you can see as we go to larger area sizes and longer durations, the West Coast tends to win. But we certainly have the market cornered on the shorter duration, smaller storms. In fact, if you look at 3-day storms over 1,000 square miles, 3 of the top 4 occurred in the past 3 years. So that's a rather impressive recent statistic. And of course, the reason that Harvey, one contributing factor to why Harvey was so wet is the fact that it moves so slowly. This is not Harvey. This is Tropical Storm Laura. Tropical storm at the time was forecast to intensify to hurricane strength and make landfall near Lake Charles. So this is actually a very good track forecast. But I want to compare that to the forecast for Hurricane Harvey by NHC that was made precisely 3 years earlier to the hour. And there's the Harvey forecast. And the difference in speed is quite apparent. If you don't remember how remarkable that stall was, we had a reminder last week. Tropical Storm Beta is fairly similar. In both cases, the 5-day track envelope pretty much encompassed the initial position of the storm. Now, in reality, by 7 p.m. Tuesday, Harvey was not sitting over Houston. It was basically on its way to southwest Louisiana, pretty close to where Laura ended up making landfall. So one of the things that Harvey did for us as a meteorological community is it showed us what could happen, what the worst case scenario seemed to be in terms of rainfall. But in fact, there are lots of things that could have gone even worse with the storm that would have produced even greater event. And so it's useful as an exercise to just sort of try to imagine what that sort of more intense event might have looked like. So, as I mentioned, the forecast track was actually had it stalling to a greater extent than the actual event did. Here's a plot of all of the forecast tracks from um, the NHC or Hurricane Harvey, starting with the forecasts that were made on the 24th of August, and it's a bit of a spaghetti plot. They all had basically the same general idea. Um, Within a couple days before landfall, it was clear the storm would stall somewhere near the coastal Bend region, and then eventually probably lift off to the northeast. The dots are timing benchmarks, so that every forecast agreed that on 0Z on the 26th, the storm would be on its way to making landfall, and in reality, it was right here at that time. Once you got past the initial forecast, every forecast agreed the storm would stall somewhere in this region, and that turned out to be pretty accurate. The actual position of the storm at that time was in fact over here, so it was already moving out a little bit faster than. In fact, it was about to cross into Matagorda Bay at 0Z on the 28th, and 0Z on the 30th of August, where I showed you the forecast track ending in Clear Lake, Texas. The actual position was out here. And all these green dots show that every single NHC forecast prior to the verification had the storm moving more slowly up the coast. Some of them had it inland, some of them had it offshore, but all of them were farther west than actually happened. So those forecasts were plausible outcomes. They were based on model simulations that were physics based as well as statistics based. So Harvey could have moved more slowly than it did. So what does that mean in terms of the precipitation and the impacts? And that's what this study is about. So first off, let me remind you what the precip patterns looked like. And it seems pretty clear from looking at this pattern that the coastline was playing a large role in where the precipitation was focused. It was mainly in a band about 50 miles inland from the coast, presumably coastal convergence due to the change in frictional contrast, as well as a weak stationary front that, according to some analyses, was set up along the coast, was contributing to focusing the precip there. So we can't just say, well, gee, if the storm were like centered in Austin, this precipitation would have occurred east of Austin. It doesn't work that way because the geographical circumstances would have been different. But in one respect, we could say that things would have been similar in the sense of a storm sitting over Matagorda Bay would probably be producing basically the same precipitation pattern as a storm sitting over Galveston Bay, because the coastline is fairly straight on the scale of the storm. There's not much topographic variation in that region. So as long as you don't get in close to the terrain of Mexico, you can probably just say if the storm was along the coast in a different position relative to this northeast southwest axis, it probably would have been producing the same amount of precipitation, the same basic pattern. So what we did was imagine hypothetical storm tracks that were similar to the NHC envelope, but kept the same position into the northeast or southwest. So, for example, these three colored tracks that I've added here are hypothetical tracks that had the storm moving more slowly, making landfall about the same place because the forecasts were consistent with that, but moving more slowly after it stalled and started taking off again. And so we have hourly precipitation analyses, and we simply displaced each hour's analysis to correspond to the hypothetical storm track under these altered locations. The ones I'm highlighting here turn out to be the tracks that maximize the total point precipitation over all the storm. And in green and brown, they maximize the precipitation in Addicks and Barker reservoirs, which is reservoirs where people were living and lots of homes got flooded. So let's take a look at how the precip does change so we can visualize what could have happened if NHC was correct, in a sense. So this is the actual precipitation distribution according to the analyses. The dark green cutoff here is about 32 or 33 inches. And you start getting into the oranges above 50 inches. That's what happened. If we slow the storm down slightly, precipitation is displaced a bit more to the southwest, as you'd expect, and it's a bit more concentrated because the precip is falling over a smaller area. Slow it down a bit more, you get this. Slow it down more yet, this is our maximum point precipitation. 87 inches near Chocolate Bayou in Brazoria County. So 87 inches is well above where I'm sitting. Of course, it's probably an overestimate given that it's based in part on the 60 inches that were quote unquote observed in Port Arthur, but 80 inches plus is probably a reasonable number. This is the pattern that maximizes the precip in Addicks and Barker reservoirs. Compared to the actual precip, you can see it's more concentrated and we're getting 50 to 60 inches of rain over this whole area. So Fort Bend County, imagine averaging over 50 inches of rain. That was a possible outcome. All along the Brazos River from Hempstead to Lake Jackson, at least 45 inches of rain. That was a possible outcome. To look at the implications to those reservoirs, I collaborated with Huilin Gao in civil engineering and her student Shudong Lee. And they ran a hydrologic model to look at what would have happened, both with a different track and if, say, for example, they hadn't had urbanization or if the rain that occurred in early August hadn't happened. Turns out changes in the track of Harvey are the ones that have the biggest effect by far. And compared to the control, which is in black, and the other simulations, you get prolonged inflow into the Barker Reservoir and Addicks Reservoir, which is not shown, for an additional couple of days. Total inflow is higher by about 40 to 50%. Peak volume in terms of acre feet is about 30% larger in both reservoirs. Peak surface area increases by about 20 to 25%, which doesn't sound like a big deal, except in this case, we're talking about a cumulative 10,000 acres of suburb. So the flooding would have been quite a bit more widespread as well. And peak outflow would have been greater also, so there's more downstream flooding with this scenario also. So I think this sort of thing is useful for imagining the worser case scenario. If Harvey was the worst case, no, it could be worse than that. And I want to emphasize this is not the worst case hypothetical scenario because we're only changing one aspect of the storm, the motion along one dimension. Other things could have been different, like the location of landfall that would have moved the heavy rain in a different place and so forth. And this is all, by the way, without climate change. This is what the storm under the present climate could have done. So we can imagine the worst case in the future would actually be different from the worst case today. So thanks for hanging around an extra day for my presentation. I'll be happy to answer questions.
No, just no questions in the chat. Let's see. I will say, as someone who grew up in Port Arthur, it doesn't surprise me that we're trying to cheat our way to a record. But and also, it could have been worse. So does that mean 2020 can be worse as well?
Well, fortunately, beta didn't turn out to be that bad, so that's a good thing.
Yeah. Well, sounds good. Thanks for being patient and being willing to give it today. So we were glad we were able to get it in.
Yeah, me too.
All right. Looks like our next presenter is in here, Tyler Wickstrom from Texas Tech University. Now we're really getting to the wind aspect of this session. Harvey was more marine flood water talk from yesterday, but Tyler's going to be talking about the validation of high resolution near surface wind forecast in North version 3.
All right. Hopefully everybody can see my screen and hear me. So I'm going to be talking about near-surface wind forecasting, and I'd like to acknowledge all of my co-authors, especially those that were instrumental in the collection and processing of the observational data that we'll be using. So a little bit of background. Accurate high-resolution simulations of near-surface winds are going to be needed for a variety of applications. These are for things like wind power estimation, structure design, operational forecasting, etc. And you can insert your own need. We need accurate simulations, regardless of whether that's for forecasting or post-event analysis. And to get such simulations, we would often use a dynamic atmospheric model. And along with some increases in computational resources, as well as increases in the accuracy and abilities of these models, we can now run in higher spatial and temporal resolution. However, even with these increases, we still need to parameterize boundary layer, surface, and surface layer processes. And so that begs the question as to what configuration of spatial resolution, temporal resolution, and parameterization configuration might result in an optimal simulation of near-surface winds. So a few more details about the model that we're using in this study. We're specifically using the weather research and forecasting model. This is a non-hydrostatic model with a 3D gridded representation of the atmospheric flow. We'll use a nested grid strategy, which allows us to achieve high resolution while also comparing the ability of different grid resolution to resolve wind structures. Initial and boundary conditions are provided by the global forecast system, and we are not doing any additional data assimilation. The model integrates in time by solving differential equations and using spatial discretization and time stepping schemes to give us a forecast at a future time from an initial point. With these differential equations, we also need to use parameterization schemes to account for unresolved processes, and this is mainly things like boundary layer turbulence and cloud microphysics, as well as radiation. And so the model can solve directly for prognostic variables like winds and temperature, pressure, and then can calculate other diagnostic quantities of interest. And so really what we're hoping to do with this study is to take a variety of configurations and model across horizontal grid scale, vertical grid scale, and boundary layer parameterizations and compare those with observed winds. And this is to help us understand the accuracy of these simulated wind fields near the surface, as well as develop statistical relationships between the simulated winds and the observed winds. And we will be primarily focusing on the first point in assessing the accuracy today. So the test case that we're going to be working with comes from May of 2019. This is a clear air data case that was collected at the Reese facility just to the west of Lubbock. We have 200-meter instrumented tower data, Ka-band Doppler radar observations in a dual Doppler configuration, as well as sticknet observations, and you can see the configuration there at the top. Primarily, this will focus on comparisons with the 200-meter tower, as well as the dual Doppler observations, which gives us a three-dimensional wind picture. And as I mentioned, these are clear air conditions. We had mainly southerly winds, not a terribly windy day for West Texas standards, but we did see winds in the 20 to 30 meter per second range, especially above the surface. So looking first at the tower observations, this is a 1 minute average. The tower takes data on 10 levels at 50 hertz, and so we average that to about every 1 minute to get an idea of some of the more mean wind structures. So that's what's plotted here. A couple of features to note: primarily, the largest wind speed observed would have been somewhere in the 20 meters per second range at a 1 minute average. We see a lot of texture and gustiness to the winds in time, and there's a defined surface layer down in the lowest two levels at 4 and 10 meters. So if we start to look at some of the model data, we can see some large differences across the horizontal grid scale as one would expect. So we're running 3 domains, the outer domain at 4 kilometers, middle domain at 1 horizontal scale decreases, the observed wind structure does increase. So we see more gustiness to the winds, more variance to the winds as we decrease the grid scale. We also see more of a surface layer in the smallest 444 meter domain, whereas we don't have much of that in the larger domains. And this can be seen if we average the plots here and take a single quantity for both variance and mean over the observational period. We can see that the smaller the domain, the larger the wind variance, while the mean wind speed tends to stay the same across the 3 domains. So increasing the horizontal resolution does seem to give us an increase in the resolved wind structure. However, I will note that we're only getting a variance on the order of 4 meters squared per second squared, and the tower observed variance closer to 15. So we're still much too low on the variance, but it does seem to give us an improvement to decrease the horizontal scale. If I consider the vertical resolution, we can look at a variety of configurations, increasing levels near the surface, so below the lowest 200 meters. So we start with 3 levels, increase that to 5, to 9, and to 15. And what we notice is that at 3 levels, there's not very much information near the surface. The lowest level is at 25 meters. We don't see any of that surface layer. We start to see some of that when we increase to 5 levels, but that really comes in around 9 levels, where our lowest model level is now around 4 meters above the ground. And we see some of the surface layer, much more of the temporal variability. But increasing to 15 levels does not seem to help that, and visually it looks like there's a little less variability with 15 levels, and that's actually seen when we consider the summary statistics. The most variance is seen for 9 levels in the vertical below 200 meters. I should mention there's more like 40 to 60 total model levels, but this is only considering the number nearest to the surface. Boundary layer parameterization, we ran a variety of common schemes, the MYNN, the YSU, the Xinhong, which is a scale-aware parameterization, and the MYJ. And generally speaking, the MYJ performs superior. Visually, it's much more realistic compared to what was observed in the tower data, and it tends to have much more variability temporally, and this is also seen in the summary statistics. Unfortunately, the lowest performing parameterization scheme was at MYNN, which is what's used in the HRRR, and so that's not so encouraging operationally for using HRRR data as a predictor of model or of near surface winds, but we'll see that may not be quite as big an issue. So one thing that we might ask is, how frequently should we save our model output? So the model is integrating forward in time at each time step, and that the time step length is determined primarily by the horizontal grid spacing, the vertical grid spacing, and the wind speed through the CFL stability criterion. So in general, we can't change the model integration time step. However, we can change how often we save output from our model, and it's common currently in operations to save on the order of 1 hour, 3 hours, 6 hours. And often for research purposes, this will be done more frequently. 15 minutes, 30 minutes is common. But how often does one have to save to maximize the variances taken from the model output? Here we have on the left a plot of each domain in the different colored lines. We've taken the full time series of wind at each model integration time step, and then we've downsampled it at 10 seconds, 30 seconds, etc., out to 60 minutes to simulate what it would look like if you changed the frequency of saving data from the model output. What we really see is that anything below 1 minute, the model doesn't really add variance to the resolved field by saving more time steps. But once you start to save less frequently than 1 minute, so 10 minutes, 15 minutes, 60 minutes, the variance in the time series starts to decrease fairly rapidly. So much so that by the time you get out to 60 minutes, if you only were to save that 444 meter domain every hour, you would have less variance than if you kept every minute of the 1.3 kilometer domain. And so at that extreme example, running the 450 meter domain doesn't even improve the simulation. So it appears that how frequently the model output is saved is very important to the final variance that will be available in the model history. The other thing to note here on the right is that for certain combinations of boundary layer scheme and vertical resolution, downsampling, saving your output less frequently, can actually add variance, and this would be noise that it's adding simply due to the filtering effect of downsampling the time series, and it's not actually real variance. And in one extreme case, it nearly doubles the variance resolved simply due to that filtering effect. So now let's take a look at our best configuration for this case. On the top is the model configuration, 1 minute average of wind speed, and the bottom is the tower. We can see some similar structures between the model and the observations, especially in regard to the temporal variability of the wind speed. We see that the tower generally has a lot more variability temporally. The tower also has a much more detailed near surface layer and a higher mean wind speed overall. And if we look at the variance over 1 minute, we can see a couple of things. First is that if you notice the scaling on the color bars, the tower has about 10 times the variance that is in the model. But the other thing we see in the tower variance is the concentration of variance in the lowest levels, whereas the model tends to only have variance changing temporally and not vertically. We can look at some individual levels. So this is 10 meter wind speed average to 1 minute. And we see, like in the previous plots, the tower has a generally higher resolved wind speed, as well as higher resolved max wind speed. And again, looking at the variance at 10 meters, we see a much higher variance in the tower. And this is really where the model struggles, is trying to capture that low temporal change in variance. Looking at some average profiles vertically over the entire observation period, the mean has a similar structure between the model and the tower, although the model is underdoing its prediction of wind speed. While the variance, again, we see that the model has no ability really to resolve that near surface variance. So just for fun, we can take a look at a gridded representation of the innermost 444 meter domain running through time. So this is every time step saved on the left there. What we see is that generally in space, we see a similar representation to what was seen for those individual comparisons with the tower. And there is some fairly good variability in resolution of gust structures in time, though it's very smooth in space. And then over on the right, we still have very little variance, no matter how we look at this, whether a single point in time or looking spatially in time. We can compare that same grid to our radar data. These plots show you the same thing. One has the model represented with wind barbs. The other has the model represented as the same color fill as the radar data behind it. Generally speaking, the radar, it resolves a lot more spatial texture to the wind field. It also seems to show that we may have an issue with our mean wind direction, whereas the model is a little bit more southerly, and the radar data appears to show an observed wind direction more southeasterly. And so some quick conclusions. In general, we see the highest variance in the model for the 444 meter spatial resolution, 9 vertical levels in the near surface below 200 meters, and the MYJ parameterization. But this higher resolution only minimally improves our simulation. The data save frequency is important. As I showed, we need to keep our output time around 1 minute to maximize the variance. And this is generally speaking independent of the model grid resolution parameterization scheme or time step. The best configuration does resolve some of the observed wind structures, and we're looking at some statistical correction options for improving the simulation. And then finally, I'll just note we have a couple of other cases. We have a thunderstorm case from May of this year that we're hoping to look at. And we did get a successful deployment on Hurricane Laura earlier this summer and got some great data from both the StickNets and dual Doppler Ka scanning. And so with that, I will leave it for questions.
Thanks for that. Thanks for that presentation. Just one comment, I think. Ted Ryan says it's not something we think about much looking at wind forecasts, so he looks forward to the convection and tropical cases.
Yes, that convection case should be really interesting.
Good. Awesome. Thanks again for joining us. It looks like our next presenter is already here, Sandeep Pal with Texas Tech University. His presentation is on the impact of horizontal advection on boundary layer dynamics across complex interfaces. So if you want to go ahead and share your screen and go ahead and take it over.
All right, can you see my screen? All right, good. So I'll be talking about on the impact of horizontal advection on the boundary dynamics. I would like to thank to my co-authors here first, and there are some of my students also, like other colleagues here. And the main research was funded by the Texas Tech University Faculty Research Startup Grants, and also some portion of NASA grant. And two of my colleagues were, supported by the Pi-Square program of Texas Tech University. So what is atmospheric boundary layer? It's too late to talk about that, but I think it's just mainly think about that two of the forcing that actually drives the boundary layer have been thought about. The surface forcing from the down, and you think about like a cellular sponge. It's been squished between the top of the boundary layer, and you also have the other source like mechanical turbulence by the wind shear that also works. So traditionally, that the boundary layer cycle has been worked for more than 50-60 years. One of the work that has not been done was basically how does the advection or horizontal advection actually drives the boundary layer physics as well. So my research question is kind of an umbrella work here. I'd like to show like how weather systems modify atmospheric boundary layer features and vice versa, and what are we missing, like instance like another air mass coming to the local boundary layer processes, and then how does it impact the scales of boundary layer kinematics and the flows. And what are the key atmospheric boundary layer features over a complex arid region like West Texas, and also how can we do better weather predictions and air quality forecasting using these high resolution measurements. So once we have the better observation, what should we do with respect to the numerical simulation? We can fix the model, basically using the improved model physics like Tyler was talking with the different parameterization. We can kick the model like using data assimilation to push the model around. And we also can quantify the calibrated ensembles of like large set of ensembles that other presenter talked about. So there is enough opportunity to, if we have a better process study, we can guide the numerical simulations. That's pretty much the overall idea here under the umbrella of advection. So the notorious term, why do we care about that? Because in atmospheric motion, with all the scales are interacting to each other. So even with the vertical fluxes, the main portion of the advection cannot be neglected. So in the essence, we need to also consider the advection of the volume of air that is passing over to another region. So that's pretty much we'll talk about like an entire ABL is being advected to a new ABL, and then how do they interact? That's pretty much the whole idea of this new research we are working here. So that basically brings the footprint concept, like that ABL processes will not only by driven by the surface forcing, but also the horizontal advection of mass, momentum, and energy. So kind of would like to share about the representativity, what we measure. So that's the whole idea of the local change of the ZI, that is boundary layer depth itself. So it is, you can see in this equation, we have a Z component, Z component here that is also being advected, and how does the intermittent mixing and subsidence take over, and then regulates the boundary layer over locally. That's pretty much the idea. And you can see delta Z, delta XZ, that's the advection term we cannot actually measure, but we can interpret. How can we do that? So let's imagine 3-4 complex in extreme scenarios like, urban-rural interface, where, and also land-sea interface, complex terrain and adjacent plains or valleys, and also frontal environment. These are the most common 4 extreme scenarios that you can think about where advection will be dominating the local boundary layer processes. So once when we have a conceptual framework, we can actually understand the boundary layer convergence line that is a trigger to the convection initiation, and across a complex of interfaces like sharp moisture gradient across vegetations, convective boundaries over arid region like here, and also land lake contrast, and all those 4 like I talked about in the last slide. So finally, we can actually make better convection nowcast using the better model physics and also advection term considered. So for instance, in the arid semi-arid region where vegetation covers kind of have a huge contrast both by natural processes and anthropogenic processes that change very rapidly even when from season to season, like that forest fire is right now happening there. Okay, so one of the first example I would like to set here, the urban-rural interface, that is like, this is the map of temperature as near surface temperature from the last 2 months ago, 14th July, that is spell of week of heat wave that we have in kind of a experienced here. So urban heat island has been worked pretty densely. Urban downtown has a higher temperature, and the rural suburbs have lower temperature. That has been well-established fact. But here in this map, you can see that in the northwest portion here, actually northeast portion here, that you can see that Lubbock Airport is getting a pretty high temperature, like we have a warmest night that we got. So nighttime phenomena, UHI. So where here we'd like to introduce the term urban heat advection. That is, if you have a pretty much southwesterly domain flow, then the source of heat is Lubbock City itself, and then how does heat advect over the rural region, and then modulates the UHI. So it's not the UHI work, but itself how the heat advects to the other region and actually discriminates the UHI from it. So that's pretty much one example of the advection here. Second example, I just worked with all the radio sound stations in the United States and National Weather Service. And then we just choose like Pacific, Gulf, and the Atlantic coast. We can see about the dance of the onshore flow and offshore flow all around this. And if we think about that, if we measure boundary layer depth using the regular basis, and we just, make the kind of separation of the onshore flow versus offshore flow, how does that picture look like? This is an example for Tallahassee. Here you can see the windroses here with respect to the windroses made by the boundary layer wind measured by the radio sound itself, and the color is boundary layer depth itself. So you can see onshore flow has pretty shallow boundary layer, marine boundary layer, and then it's advex over the land, and then you have a contrast, pretty strong contrast in the offshore flow versus onshore flow. And that has been, people when talk about this is seasonal scale, these all differences are kind of smashed in, and that actually gives the wrong results for instance. So now if you summarize for all these sites all around the US, for all 3 coast region here, main regions, then you can clearly see the offshore flow has a pretty dominant in the same color scale here, and then onshore flow have a pretty bluish kind of thing that you can regularly see that event every season. It's not only one season event. So that is a kind of a showing that perfect match that advection matters for coastal region. Then third type of example, like think about the complex terrain and adjacent plains. We have a mountain advected wind, elevated residual layer that actually goes over the adjacent plains and then delays the convection. How does this whole process of the mixing between the current ABL and the overlying residual layer actually interacts with each other? That has been not reported pretty well in the literature. So what we took we took the radio sound observation and just choose the sites in the downwind of Rockies and also Appalachian here, R and A, and then we studied the same concept of the downwind of the Rockies, and if the wind is coming from a flatland, then how does that work? So then you can think about this one example, Great Falls, Montana. Here you can see the windroses with respect to boundary layer depth here in the color coded. You can clearly see that ZI mountain downwind versus ZI flatland downwind. You have a pretty much strongly related towards like you have like strong mountain downwind impact, that you have always that westerly impact or downwind from the mountain. So that is happening every kind of season. That is a pretty striking evidence of the advection of the residual layer on the local boundary layer processes. Then we do the same process for the whole season and then show that. And you can see on the right side of the flat line wind versus mountain downwind. You can see the strong contrast here as well. And then fourth example is the textbook example, the frontal passage. You also air mass exchange happens. Now think about it. If we cross these fronts, if the aircraft measurements, and then you go back and forth, you can actually get the boundary layer physics in the warm sector and also in the core sector. And within a funded project here at Texas Tech, we also had a long record of flights within a project that we have gathered the cloud physics LiDAR observations along the frontal boundaries. And using that, we can actually see the physics of the boundary layer in the both warm sector and core sector and how do they differ and understand the physical mechanisms there. So one example here, you can see that frontal boundary was pretty much somewhere here, northern Nebraska. You can see for this example, we have like a pretty much higher boundary layer depth in the core sector than in the warm sector. Pretty much you can think about like, you have a cloud radiation actually impact the boundary layer physics on a different day. Then you go for like tower-based observation or the radio sound observations. Again, we choose like frontal passages from National Weather Service and our WPC map, and we analyzed like more than 17,000 radio sound profiles and more than 14,000 surface map, of course, by machine learning here. And then we took about like a 200-kilometer radius of this distance around this shown here. Then you can actually see when the prefrontal versus day of front and versus the post-frontal kind of condition. How does the boundary layer dynamics dances here in this kind of scenarios? So that actually gives you a strong evidence here. This is the left map here shown all those sites, which is not impacted by the onshore-offshore flow, which is not impacted by the mountain flow, which is not impacted by the urban flow. So we choose those sites along this region. And just to discriminate the frontal impact chosen on this region from the Midland to International Falls, all around the region. One thing is clear that this is the first evidence that we are seeing this frontal contrast in the boundary layer depth, and that also has a inter-seasonal variability in itself. So that's a new information that we are learning at this point, and how to actually tackle that with respect to different atmospheric scenarios with respect to model physics there. It's pretty unknown under the impact of advection here. So then going back to the urban-rural interface, contrast in the ABL dynamics, it's a kind of a note again, like we are working on it and we are looking for collaborators and also for funding that, and that one of the example I gave you the heat part, but now all the results you have seen here so far looks like a point measurements of radio sound profiles. Now, if we have a scanning LiDAR system like we have a Doppler LiDAR that you can scan along the interfaces or across the interfaces, you can get the thermodynamics as well as boundary layer dynamics in more detail, like the example here, you see the radial velocity, then you can get more high resolution information and kind of tackle those problems in high resolution mode. And again, get to the problem, how does the instantaneous field of this dynamics of around the boundary layer across the interfaces looks like. So take-home messages, a conceptual framework has been developed to examine the impact of advection on the ABL kinematics. We have new empirical evidence in the contrast of ABL dynamics with respect to land, sea, mountain plain, and across frontal boundary. And these are encouraging and provides enough confidence to develop further numerical parameterization schemes in the model. And I think I would like to stay with the same last message here. Even for small city, advection of urban heat matters and affects the resultant UHI scenarios. And thank you very much for your time in the late Friday afternoon.
All right, thank you. We actually had one question come in. He said, I honestly have never thought about the urban heat island advection. Have there been any studies on this over the DFW area?
Yes, right. Thank you. That is a good point. We have 3 or 4 types of heat island part of the urban region: urban heat island, urban pollution island, urban wind island, as well as heat advection going towards the region that is whether matching to the DFW or big cities. But we would like to see that for even small city like Lubbock, that matters. And we'd like to see in the extreme heat event that we saw, one of the examples that I cited. But this work is undergoing. We don't have a strong evidence with respect to boundary layer dynamics yet, but that's what we're working on. Thank you.
Awesome. Well, thanks for joining us. We appreciate you taking the time to be a part of our conference. Looks like our next presenter has already joined us, Samantha Whaley. Did I say that right?
Yeah, it's Wally.
It's one or the other. She's with Texas Tech University, and her presentation's on exploring spatial variability of columnar content of CO2 across frontal boundaries using airborne LiDAR observations. So looks like you're already set up and presenting, so I'll let you have it.
Hey everybody, my name is Sam Wally. I am a grad student here at Texas Tech. Like you said, I'm going to be presenting a little bit of information about the spatial variability of columnar content of CO2 or XCO2 across frontal boundaries using airborne LiDAR observations. So a little bit into our research goals before I get too in depth. The main goal here is to understand how air mass transport via synoptic systems affects XCO2 spatial variability. And by doing so, we're going to demonstrate the potential of using the MFLL LiDAR to explore these frontal contrasts in XCO2 so that we get the full column of CO2 in all 4 different seasons. And so a couple questions we have is we want to know how the XCO2 frontal contrast change in the 3 different regions that we have data from. That is the Midwest, the Mid-Atlantic, and the Southern US. We also wanted to look at what are the typical spatial distributions of XCO2 variability in both synoptically benign and synoptically active environments over the 3 Actamerica regions that we use the data from, and also the 4 seasons. And another feature we'll note that later on in the presentation is what meteorological features may enhance the XCO2 at the frontal boundary itself. And our last question, which we won't include for the sake of brevity in this presentation, but we have already conducted, is how well the WRF-Chem simulations and the GMAO curtains agree with observational findings. So a little background information on Actamerica. ACT stands for Atmospheric Carbon Transport. And there are several different mission goals, but our main objective here is to quantify and reduce atmospheric transport uncertainties. And so by doing so with the XCO2, will definitely help with model observations. So a little background information as to the CO2 variability in fronts. Powell et al. 2019 investigated the variability of CO2 across the frontal boundaries using in situ measurements in just the summer of 2016. And variability in CO2 was seen due to both mesoscale and synoptic scale features. And one important thing to note here is that the pattern between warm and cold sector is always, the warm sector is always higher than the cold sector in CO2 in this case, for all days in the summer. So a little bit more into our data collection. There was obviously 2 aircrafts here. One was the C-130 that housed in situ instruments, the MFLL LiDAR, along with the cloud physics LiDAR. And then the other smaller aircraft was the B-200 that only flew with in situ instruments and usually sampled lower altitudes and our boundary layer measurements. So we are using the multifunction fiber laser LiDAR, which is always a mouthful, to collect our XCO2 measurements. And this LiDAR provides us with the full column measurements that we take the LiDAR optical depth measures and get the XCO2 measurements, and it provides us with the full column information about the XCO2 observations. So there is a slight problem, but also a slight benefit with using XCO2. So in this image here, you can see that we usually have observations around 6 kilometers for our upper level. And along that flight path that we are going to be flying through a frontal boundary, we have constant in situ measurements. And also along that boundary, we're also getting constant LiDAR measurements. So when you're well into the cold sector of the front, we know we're going to be sampling cold sector for the entire column. And we can do the same thing for the warm sector once you're on the other side of the front. Problem is at the front, we don't necessarily know what we're sampling as far as warm sector and cold sector. And so we see some interesting features with some enhancement in some regions and some not enhancement in some regions. So this is an interesting predicament that we have here. And we see the same thing at 3 kilometers. And a lot of the times we end up using the 3 kilometer data because there's more data available from the XCO2. A little more background information. I have 4 seasons. 3 regions, which you can see here in the blue. And out of a total, we have 26 cases with frontal days. There are plenty more CO2 days from Act America, but they're not all frontal cases. So we still have a pretty good data set here. And I did want to give one sample case. This image here on the left is the flight path. The red is the in situ measurements, and the blue is the B200 flight path. We can see we're crossing over a stationary front, cold front, across the front. And we can see here in the box and whisker plots, along with the histogram, there's a clear distinction between the warm and cold sector. But one interesting thing to note is we have some mixing here between the cold and warm sector, where the cold front should be. But then this could be due to us sampling that full column measurement, like I said. So a little bit more into calculating our frontal contrast, like a total seasonal frontal contrast. I used the furthest half-degree latitude box, and I took the mean of that box, and then for both warm and cold sector, and compared those. I chose the furthest half-degree because this allowed us to ensure that we were sampling the cold and warm sector and not the frontal boundaries. However, as much as we'd like that to be ideal, there are a few cases that we could be sampling some of the mixing at the frontal boundary itself, but that's something we're still looking a little bit further into. So for the sake of brevity for this presentation, I'm just going to show our summer and winter cases. Our summer mimics Powell et al. Pretty well. This work, we see the warm sector is higher than the cold sector, and I think underneath here we can see that our delta XCO2 is around 6.5 ppm for the entire season. And then winter, and this tends to be similar to what we see in fall and spring, is there's no clear pattern, and this is due to a lot of the transition seasons, and growing days, and dormant days, and that kind of stuff. And so this is not, you don't have as clear of a pattern as summer. But we can still see that there is an average delta XCO2 of around negative 1.3 ppm. So again, now looking at the frontal boundary itself and the enhancement region we see, I want to look at it in 3 different ways. And this is a little bit more preliminary work here. We haven't actually quantified anything. But we're going to look at it in 3 ways. We're going to look at the distance of the enhancement, and then we want to look at the area and the mean of the enhancement subtracted from the warm sector mean, and then we also want to look at if there's clouds or precip near the boundary that could be enhancing some type of mixing or some type of cloud effects on the actual CO2. Again, one key idea to remember here is that the MFL is sampling that full that full column at the frontal boundary itself. The variability at the frontal boundary is seen in many of our cases. However, with limited data, at a lot of these, really only 6 days have sufficient data for calculations. And so I have a couple examples of these. This is our August 4th, 2016 case, and there is an evident enhancement in XCO2 near the frontal boundary itself. We see that clouds are present, and I'm pretty sure this day also had precip present. And we can see we're sampling a cold front, and we see that ideal enhancement here at the frontal boundary. And so when this area of enhancement right here is compared with the entire mean, it's about 1.6 ppm higher than the actual mean. And this October 5th case, again, this is a very small but pretty strong enhancement that we see here. Again, we have clouds present crossing a stationary boundary, and again, we see that strong enhancement in our box and whisker plots. And the distance for this enhancement is not very large. It's not but a half degree, around 55 kilometers. And the difference between the enhanced region and the mean of the warm sector is 12.16 ppm. So this one is a strong case for the enhancement itself. And a little bit of a summary. So one important thing here to note is that we see clouds with every single one of these cases. And so there must be some type of correlation with it. We just haven't fully delved into that. And we see precip with most of the cases. And even in these 2 cases, there was precip in the area. It was just a good bit off from where the actual front was and where the flight was at the time. So into my conclusions. So we see across 4 seasons in 3 different regions, there is a frontal contrast with every single flight leg in XCO2. Summer obviously has the clearest pattern due to its extremely low CO2 and the transport of different air masses into the region. And our work did agree with Powell et al. 2019 just for the full column. And like I said, the other seasons have more variability as far as a pattern goes. And this could be attributed to the growing seasons and varying in each region, and along with air mass transports, like I said. The XCO2 enhancement near the frontal boundary is likely sampling the MFLL in both cold and warm sectors, so that's why we have some enhancement in both cold and warm at the frontal boundary itself. And like I said, there may be some correlation between clouds and precip in the XCO2 enhancement. So a little bit of future work. We have already conducted comparisons between the MFLL, XCO2, and WRF-Chem simulations. And this work is going to help us understand the biases in the model that are in reproducing these frontal structures in XCO2. We're also going to compare with the GMAO model, which we just got. And this GMAO is going to provide us with a curtain to help us look better at the frontal boundary enhancement in CO2. So hopefully we can get a little more information about that coming soon. And then we're also going to do a case study for 4 specific seasons, looking specifically at meteorological conditions and the cloud physics LiDAR observations to help understand those XCO2 frontal enhancements. And we're also going to use the GMAO curtain and a WRF curtain to investigate those. And I just want to say thank you to NASA and Act America for the funding, and also Dr. Paul and Texas Tech for letting me be here. With that, I will take any questions.
Thanks for the talk. We just had one comment. He had a question, but he said your conclusion slide answered his question. So with that, there are no other questions. So we thank you for taking the time to join us. Really appreciate that. Great presentation.
Thank you very much.
Their conference, and that honor goes to Mary Kelly with Texas Tech University. And her presentation is more towards the dust of yesterday, but it's an examination of the patterns of blowing dust days in Lubbock from 2000 to 2019. And with that, we'll give it away to you to go ahead.
All right, can you see my presentation and hear me? Okay. So thank you for the introduction, and thank you to everyone who's staying this afternoon, late on a Friday. Like you said, I will be talking to you about dust storm events that occur in Lubbock, Texas from 2000 to 2019. Like was said yesterday, Lubbock is very prone to dust storms, and so I'm just looking at the different variations of these dust storms that occur in Lubbock. So first, a dust storm is a meteorological phenomenon where strong winds pick up loose particulate matter and transport it far away from its source. So many factors contribute to dust storms, but of course, the most important is wind. And these winds that are associated with dust storms are a result of 2 different types of meteorological disturbances. The first one being a synoptic disturbance, which is just a scale used in meteorology that is few hundreds of kilometers above the surface. And synoptic disturbances can include things like warm and cold fronts, low and high pressure systems, troughs and ridges, as shown in this picture right here on the right, or on the left, sorry. And the second one is convective. And this is just any quick increase of winds that are associated with thunderstorms that includes outflows, micro and macro bursts, and downbursts. So the study of dust storms is important just due to the hazards that are associated with them. The most important one being health. The particles in dust storms, when a person is outside and exposed to these dust storms, they can actually inhale these particles. And looking at this chart right here, bigger particles will stay in your upper respiratory system, possibly causing allergies, maybe a little bit of asthma. But smaller particles can actually make their way down into your lungs and can possibly get absorbed into your bloodstream, making their way to your heart and your brain, possibly causing a heart attack, stroke, or even premature death. And then also travel hazards. When a dust storm blows through, the visibilities tend to decrease. And for more intense dust storms, they can lower below a mile. So showing these two pictures right here, this one is actually from a dust storm that occurred in April of last year. And this is a multiple vehicle wreck that happened just north of Lubbock due to this dust storm. Luckily, there weren't any deaths, but there were many injuries due to this dust storm. And this one was taken at the Lubbock International Airport by the Lubbock National Weather Service employee Joe Merchant from the October 2011 dust storm. And when this dust storm blew through the airport, it actually knocked this airplane over, causing some significant damage to this plane. And then there are some hazards associated with agriculture. So with livestock, just like humans, they are able to breathe in these particles and can deal with these health problems and possibly suffocate and die just from the exposure of dust storms. And also crops. This middle picture right here shows a little baby corn stalk, and then a dust storm blew through, and you can see that there's some abrasions and cuts and stuff to the leaves. The tips of the leaves are brown. Luckily, the crop survived, but other times crops generally die just due to these dust storms preventing it from performing photosynthesis or just tearing it up in general. So like I said in the very beginning, Lubbock, Texas is very prone to dust storms. We are located in the Texas Panhandle, specifically on the eastern edge of the Southern High Plains Plateau. And Lubbock is generally known for their agriculture, especially cotton. We are 2/3 of Texas's cotton crop and 1/4 of the United States cotton crop. So for my methods, how did I identify if a day was a dust storm day or not? I used the Meteorological Aerodrome Reports, or METARs, that are put out to the public by the Lubbock National Weather Service. And these are just reports of meteorological parameters taken by the ASOS station located at the Lubbock International Airport. And this can include parameters such as temperature, relative humidity, wind speed, and direction. But another thing that they put out in the METARs is a present weather code. And this is just where the ASOS station puts in a code of whatever weather is occurring at that time. So if a thunderstorm is occurring, then the code is going to be associated with thunderstorm. Or if it's clear, then the code is going to say CLR, which stands for clear. So for dust, I generally looked for BLDU, which stands for blowing dust, DU, which is widespread dust, and DS, which is dust storm. And then I took the all the days that had dust storm or a dust storm code, and I wanted to separate them by their meteorological disturbance. And I did that by looking at the area forecast discussion. And this is another text product put out by the Lubbock National Weather Service, where a meteorologist on duty at the time just puts out a small little paragraph of the weather that is occurring at that time or what they expect to occur in the future in like the next couple of days. So I looked at all of the area forecast discussions for that dust day and determined whether it was synoptic or convective. And then for convective, I also used the present weather code again in the METARs to determine if, or to confirm it was convective by looking to see if a thunderstorm code occurred at the same time as a dust code or directly afterwards. I also use some particulate matter data. The Texas Commission on Environmental Quality has a PM 2.5 station here in Lubbock, and they started this station in 2001 and is still currently taking PM 2.5 measurements here in Lubbock to this day. So into my results, so from 2000 to 2019, I had 430 days that had a dust storm code in their METAR. And looking at just an annual dust storm frequency, there really was not a trend. So I looked at it with the total annual precipitation, and you can see that years that had higher dust storm frequencies correlated with years that had lower total annual precipitation. And looking at 2011 and 2012, those are good examples of that. Those are the 2 years that we had the highest dust storm occurrence, and they're also 2 of the lowest total annual precipitation years. And also, spring had the highest seasonal dust storm frequency. So then I wanted to compare different meteorological parameters for dust storm days to non-dust storm days. So looking at these box and whisker plots, the black box is for dust storm days and the blue boxes are for non-dust storm days. And comparing the two, dust storm days correlated with higher temperatures, higher wind speeds and gusts, lower visibilities, and lower relative humidity values compared to non-dust days. So then I wanted to look at the diurnal variation, and this is where I used the PM 2.5 concentrations. I looked at the variation of these PM concentrations specifically on the dust storm days. And as you can see in this top chart, the PM 2.5 concentrations generally increased in the morning and peaked in the afternoon around 1 to 2 p.m. and then slowly decreased throughout the day and stayed pretty low and stagnant during nighttime hours. And I also compared that to the diurnal variation of wind speeds, and the concentrations generally follow the same diurnal variation as wind speeds, which makes sense just due to wind speeds are pretty much the most important factor to dust storms, because without winds, there's nothing to pick up the particles to be able to blow them away from their source. So then I took all of the 430 dust storm 89 days, and convective had 130. I did have 11 days that were a combination of the two, which was where a dust storm was initiated by a synoptic disturbance, but it was enhanced by a convective disturbance. Now, since there's so little of those, we believe that 11 days really isn't a good amount of days to show what is actually happening during these combination dust storms. So from here on out, we're just going to focus on the synoptic and convective dust storms. So first, I wanted to look at the monthly variation just to see how convective and synoptic would differ temporally. And convective generally occurred in the summer months, mostly from May to August, and synoptic generally occurred in winter and early spring from November to about April. Then I looked at the duration to compare the two. Red is convective, black is synoptic. Sorry, I should have said that the previous slide. So for both synoptic and convective, majority of the dust storms were in the 1 hour or less category, but synoptic tend to last longer than convective, with some of them lasting up to 14 hours, while convective, the longest one lasted up to 6 hours. Then I wanted to look at the meteorological parameters of comparing synoptic and convective. Again, the black boxes are synoptic and the red boxes are convective. And comparing the two, synoptic correlated more with lower temperatures, which correlates that they mainly occur during the winter months. So they generally occur during the season that we have colder temperatures. Synoptic also had lower relative humidity values, higher wind speed and gusts. And looking at the box and whisker of the visibilities, they look generally the same, but looking at the average visibility, synoptic had a higher average visibility compared to convective. And then I wanted to look at the wind direction. So I have these two wind roses. The one on the left is for convective and the one on the right is synoptic. And for synoptic, majority of the dust storms came from the west, which correlates because majority of the synoptic dust storms actually were due to a west to east moving cold front that was coming through our area. While convective did not have a predominant wind direction, and this is just due to the wind direction is dependent on where the thunderstorm is occurring to Lubbock. So then some conclusions. Again, I had 430 dust storm days. Dust storm days did show some meteorological differences to non-dust storm days. The diurnal variation showed a unimodal variation with an increase in the morning and a peak in the afternoon around 1 to 2 p.m. and then slowly decreased throughout the rest of the day and was stagnant through the night. Most of the dust storms were caused by a synoptic disturbance. A convective occurred more in the summer, while synoptic was mainly during winter and early spring. Synoptic dust storms tended to last longer, with the longest one lasting up to 14 hours, and synoptic and convective dust storms showed meteorological differences. And thank you, and I would like to acknowledge Texas Tech University's graduate school for giving me a fellowship to be able to continue this work in my PhD. And I will be expanding this to other areas in West Texas as well as New Mexico.
Awesome, thank you, Mary. Looks like we got one comment. It would be interesting to see when dust did not occur, even though winds were high. In other words, trying to find a more accurate way to forecast when dust would occur without just looking at winds.
So that is what we actually plan on doing, like looking at other areas. We just want to take everything, put it all together, find the differences between all of it, and try to make this dust storm forecasting I guess forecasting system that that National Weather Service could possibly use, because obviously you're going to have other events that include high winds that aren't necessarily dust storm. So there's more factors that go into dust storms, but the main one would be wind.
Okay, then lastly, we had a comment that said, GOES 1617 have revolutionized the detection of dust in real time. Have you given any thought about looking at that data from cases in the last few years and investigate if there are days where it's more difficult for the satellite to observe the dust than others?
I have not done any like looking into any data with satellite. That is definitely something that I want to do in the future. This was just my master's work, but definitely in the future, I would like to do some stuff with satellite work, because I know satellites are pretty good at detecting dust.
Awesome. Cool. Thank you. Thank you for that presentation. If you want to go ahead and drop off, we're going to wrap up the conference now. Well, that concludes our conference, our 2020 virtual Texas Weather Conference. We were very thankful for everyone who stuck around until the end. We're very thankful for everyone who came over the last 2 days. Luckily, there was not many technical issues, just a couple here and there that we were able to solve pretty quick. So that was good news there. Just stick with us. Hopefully, in the spring of 2022, the pandemic will be over, and we should be back in Lubbock sometime in the spring, hopefully early March of 2022 with an in-person conference. The virtual worked great, the chat questions worked great, but nothing beats that in-person conference where we're able to see each other and talk to one another. So with that, we're going to conclude the meeting. I will send out some notes through email. I will try to get these presentations even linked up on the program as well, and I'll work on that over the next couple weeks and send that out. Thanks again. We hope you have a good weekend, and that's a wrap.